Hello students, welcome to the class. So today is the day second of this coordination compound and the 26th day of the 40 days crash course. In the previous class, we have studied about the isomerism and the nomenclature. Now, in today's class, before moving on to the topic, so this is our disclaimer. So what are the topics that we are going to cover today? We are going to see the coordination compound. Sorry for the interruption. So first of all, we will see the bonding in coordination compounds. Now in this, we have two types of theories which can explain this bonding. The first one is the valence bond theory. So we'll study about that valence bond theory. After that, with the help of the bonding, we can know what type of magnetic properties are shown by the coordination compound. So in the previous class of DNF block, I have made you remember a formula which was about the Bohr magnetron. It was root under n into n plus 2. So with the help of that, you can calculate the magnetic moment of any given ion. Now I would ask you that what was the n in that case? Okay, what was the value of n? What does it represents? Then after we will move on to limitations of valence bond theory. You can answer this question in the comment section. Okay, because multiple times questions are asked from this magnetic properties of coordination compound. Next, we will move on to crystal field theory. So after learning valence bond theory, we came to know that this theory was not capable of explaining the overall picture of the coordination compound. So we need something which is more closer to the bonding in your coordination compound, and hence we moved on to this crystal field theory. If I tell it in simple words, it is basically based upon the electrostatic interaction between your metal ion, which is positively charged, and your ligands, which are containing electrons and hence representing the negative charge. Next, we will study about this in the tetrahedral coordination entity. So first we will apply it to the octahedral, and then we will see about it in the tetrahedral. After that, we will study about the color composition which is shown in the coordination compound. Now there are multiple reasons for this color. Because of this, your coordination compound are found in variant color, and this is mainly due to two phenomena. The one which is very important for you is the DD transition. Okay, so basically after your splitting in the crystal field theory, your electron can jump from a lower ground state to a upper excited state, and then it reverts back emitting a color of certain electromagnetic radiation, and hence we are able to see color coordination compound. Next, we will move on to the stability constant and stability of complex. So we need to know that how does a compound represents stability and how can we compare it with the stability of other coordination compound. With the help of this, we can also know that whether that particular coordination compound will be formed or not. So it will be studied on the basis of equilibrium. Got it? We will see about it. Then after, we will move on to a very important topic, because questions are asked from this part also, which is importance and application of coordination compound. Specifically I would say that there was a question from the Wilkinson catalyst. It was asked that whether the given complex is low spin or high spin. Okay, so if you don't know the name of or the formula of the Wilkinson catalyst, how can you predict its spin? After that, we will study about the organometallic compound, in which we will study about the carbonyl complexes. Got it? So first of all, starting with the bonding in coordination compound. If I talk about the bonding in coordination compound, then this is explained by two approaches. As I said earlier, the first one is the valence bond theory. So let me explain it in detail. Here what we do, we take the metal ion, and under the influence of a ligand, your metal ion shows inner orbital complexes or outer orbital complexes. Okay, and it is happening due to the hybridization. We have studied about hybridization. We have various kinds of hybridization, sp3, sp2, then sp3d2, d2 sp3. So here in this case we will be mainly focusing on two type of geometries, tetrahedral and octahedral, and one more, square planar. Okay, so for these three we have four different type of hybridization. Okay, so first of all, the ligand approaches your metal ion. As a result of it, the electrons get paired up or not paired up depending upon the strength of the ligand, and then after, the hybridization takes place. Okay, now the hybridized orbital of your metal can overlap with the pure atomic orbital of your ligand, and hence they can create your coordination compound. Okay, so this is the first way to see the bonding in your coordination complex based on the valence bond theory. Now we will study more about it. Talking about the hybridization, we have three kinds of hybridization. So for octahedral, it is D2sp3, or in some cases it is sp3d2. Then for square planar, it is dsp2, and for tetrahedral, it is sp3. Got it? So these are the four kinds of hybridization which are shown by the three geometries. After that, if your coordination number of 6 is seen in the compound, then two types of hybridization is seen. So one is mentioned here, D2sp3, the other one is sp3d2. In both the cases, the number of orbital is 6. Therefore, the coordination number is 6 and the shape is octahedral. See here, 2 d orbitals, 1 s orbital and 3 p orbital. So that counts up to a total of 6. Whereas in this case, square planar and tetrahedral, the dsp2 means 4 and sp3 also means 4 atomic orbitals. Okay, so this is the way you can see the hybridization, and remember the names and the corresponding hybridization. Now we have to decide then in which case we will see d2sp3, means in which octahedral complex we will see d2sp3, and in which we will see the sp3d2. So let us look about that part. So in that continuation, we will look upon the types of complexes. The first one is inner orbital complexes. What are inner orbital complexes? So here your ligands are strong field ligands and they form low spin complexes or inner orbital complexes. What is the meaning of this? Let us try to understand this thing with the help of a particular example. For say we are taking this cobalt and its configuration is given here, which is 3d7 4s2. Now next we are converting it to the CO plus 3 oxidation state. So what we will do, we will remove 3 electrons. So 2 are removed from the 4s and 1 is removed from the 3d. Now this is very important. Although we fill electron first of all in the 3d and then in the 4s, but when we remove the electron, we always remove it from the ultimate shell or the last shell. So in this case it is 4s. So first we will remove it from the 4s and then the third electron from the 3d. Next, what is the thing? So since it is an inner orbital complex and the ligand that is used up here is the NH3, and NH3 is a strong field ligand for cobalt 3+. So what it will do? It will pair up the electrons of cobalt 3+. What is the meaning of pairing here? Here in the 3d, upon the change of oxidation number from 0 to +3, the number of electrons is 6. So it can be accommodated into 3 orbitals by pairing the 2 electrons. So here what we have done, so 1 is already paired up, the remaining 4 are paired up in the 2 orbital of the 3d. Got it? Now we have a set of orbital that can be hybridized, and into it the NH3 ligand can donate its electron. So this is the way. And what are the orbitals that are involved? It is n-1d. See, it is written here n-1d, ns and np. Why I am telling it is n-1d? Because if 4s is here and 4p is here, then 3d will be involved. So that is the thing which is indicating n-1d. Here 4, so that means d will be 3d. Got it? So the overall hybridization will be d2sp3. And in this table, what will happen? Your NH3 will donate its lone pairs, okay, during the overlap of the orbitals. Got it? And your CONH3 whole 6 3+ is formed. Remember, your ammonia is a weak ligand, but for cobalt 3+ it becomes a strong ligand. We will talk about it in detail. What are strong field ligands and weak field ligands? This is explicitly explained in the ligand field theory or your crystal field theory. Okay, so here we are getting only a crux of it. Now, next, the next important thing regarding this complex is your electrons that are not paired up. So here you can clearly see that all the electrons of your cobalt 3 plus are paired up, and hence the complex that is formed is diamagnetic in nature. Now this has already been taught to you in your D and F block elements, where we saw that if all the electrons are paired up and no unpaired electron is left into the orbitals, then we say that your given complex is diamagnetic in nature. Here, anyone has a doubt in this part, you can ask it here. And remember, how we will decide that whether a given ligand is capable of pairing the electrons of your metal ion or not. So for that we will have to study about the CFT. So this is one of the limitations of your valence bond theory. It is not quantitatively explaining that which ligand will pair up the electrons of the metal ion and which will not pair up. So here it is seen that your NH3 is pairing up. Okay, in the outer orbital complex, that we will see that the pairing is not done. So that thing is something which is not explained by the VBT in this given theory. But when we will move on to the crystal field theory, we will see a spectrochemical series which compares the relative strength of the ligand. Okay, so don't worry about that. So anyone who has a doubt in this part? So I've asked you a question in the start of the lecture. So the formula to calculate the magnetic moment is root under n into n plus 2. So what is n representing here in the magnetic moment formula? Anyone, can you tell me? So those who are attending the class, can you tell me what was the representation of n for that? Because this formula is very important for your coordination compound. There may be a chance that you will be directly asked a question regarding calculation of magnetic moment. Yes, very good. So that is number of unpaired electron. Yes. Now, next, moving on to outer orbital complex. So it's very simple, just opposite of that. In this case, your pairing is not done. Okay, and we also name it as the hypoligated complex. So for inner orbital complex, there is another name, hyperligated complex, and for outer orbital, we have a different name, which is hypoligated complex. Now in this case, the ligands are weak field ligand and they form a high spin ligand. Okay, or they are called as the high spin ligand. Now what will happen here? Remember, this terminology I am using here, high spin and low spin, it is related to your crystal field theory, but for your relevance, that how do you decide that whether a given ligand will pair it up or not, I am mentioning it here. Or else only the mention of this outer orbital complex is much more relevant in the case of your valence bond theory. Now moving on to this kind of complexes, here the orbitals which are involved are all of the same shell. Now what is the meaning of this? For example, if we take halides such as fluoride, chloride, bromide, iodide, and then sulfide S2 minus, they all are forming outer orbital complex. The reason is that they all are weak field ligand. What are they? They are the weak field ligands and they will not pair up the electrons. Now, a quick example of that would be COF6 3 minus, where the cobalt is present in +3 oxidation state. Now, can you tell me if the +3 oxidation state is present here and no pairing of electron will take place? So, I am giving you the point. No pairing of electron will take place because of the weak field ligand. So, what will be the number of unpaired electron in this case? Can you tell me? Before moving on to the diagram, I am asking it to you that what will be the number of unpaired electron in this given complex, given the information that it will form a outer orbital complex. So first, try to write the electronic configuration of cobalt. Okay, so the answer is here for me. So it is 4. Anyone else who is interested to give the answer? So meanwhile, if you want, you can also calculate the magnetic moment. It's very simple. We have seen the diagram in the previous example as well. You have to only put the electrons in such a way that the pairing would not take place. Okay, so you will use the formula root under 4 into 4 plus 2 to calculate the magnetic moment also. Next, so this is the diagram. Very good. So it will be 4. So what will happen here? First of all, the cobalt will be in the +3 oxidation state. So for that, we will remove 3 electrons. Again, remember, you will start removing electrons from the 4s. Although 3d is filled first, but the electron is removed first of all from 4s. Now 4s electrons will be removed, and then the electrons of 3d will be removed. Got it? Is it clear? Now it will result in a configuration in which the 3D will have 6 electrons. But in this case, the ligand, which is your fluoride, is not that much strong. So it will not pair up the electrons, and hence the fluoride ion will donate its electron to the 4s, 4p and 4d. Now that would result in sp3, means 3p orbitals, and d2, sp3d2 hybridization. Is it clear to you? Did you get it? Why we are getting sp3d2? Because pairing is not possible with the help of fluoride ion, and hence we have to involve the orbitals which are present outside the d. So that is the reason we are calling it as outer orbital complexes, because here outer orbitals are involved in the bonding purpose. Got it? And here all the orbitals are coming from the same shell. It is not n-1d ns-np, it is ns-np-nd. So the chronology is different in a way. In the previous case, we have 3D, 4S and 4P involved. But in this case, it is 4S, 4P and 4D involvement. Okay. So as I said earlier, so the number of unpaired electrons is 4. Therefore, it is capable of showing paramagnetic nature. Okay. So this complex is paramagnetic in nature. Remember, what are the names of weak field ligand? This is very, very important to remember, because this will help you to consider that which of the complex will be outer orbital and which one will be inner orbital complex. Next, as I said earlier, that your unpaired electron is the reason that it forms your what? It forms your diamagnetic compound, and paramagnetic compound are formed from the unpaired electron. Now next, moving on to the next kind of hybridization, which involves dsp2 and sp3. Okay, what it involves? It involves dsp2 and sp3, and here the coordination number is 4. So in case of dsp2, the shape will be square planar, whereas in the case of sp3, the shape will be tetrahedral. Now we have a square planar complex characteristics. So here is the characteristic table. So if I talk about both of them, in the case of inner orbital complexes, the ligands are always strong and also known as low spin ligands. The hybridization is dsp2, whereas in this case the hybridization is sp2. Remember, if 4p is the p and 4s is the s, then the d will be of 3d in case of dsp2. Whereas in the case of sp3, all the orbitals are coming from the same shell. So here we can see 4s and 4p are involved. In the case of dsp2, what is the shape? The shape is square planar, and in this case the shape is tetrahedral. Now there is a question for you. How can you identify that whether a given complex will have a tetrahedral or a square planar? You will quickly say that we will decide it with the help of inner orbital and outer orbital complex, means with the help of your ligand strength. But here is a small twist in it. So any one of you who knows this twist, so there is a certain requirement for a compound to show a square planar complex. If it is showing that particular property, then and then only it will have a square planar shape, or else it will always have a tetrahedral shape. Anyone, can you tell me what are the requirements? So first one is already known to you. You can write the first one very quickly, which is the presence of strong field ligands. But it has also some properties requirement regarding to the metal ion. Can you tell me? So the count of electron is fixed. Then and then only it will show square planar complex. So this will help you a lot in the exam if you know this thing. Okay. So let me tell it for you. First of all, your ligand should be strong. So that is a necessary point, and it is written here also. The second point is that your d orbital must contain 8 electron. What did I say? Your d orbital must contain 8 electrons, then and then only your square planar complex is formed. Now you take any example from your NCERT book which shows a shape of square planar complex, and you will see that it always has it will always have 8 electrons in the d orbital. Can you take an example? Yes, Ni2 plus, I guess, is having your d8 configuration, and it is capable of forming square planar complex. You'll know a lot of names of square planar complex which is having Ni2 plus as the metal ion, isn't it? So did you get my point? So remember this trick, okay? This is a kind of trick to know that whether a given complex is square planar or not. You will always look upon the number of electrons of your d orbital, and if it is 8, then and then only it will form what? Square planar complex. Any doubt in this? So you can quickly take the example of NiCN42 minus. There we have Ni as D8 configuration because Ni is present in +2 oxidation state. Okay. Now moving on to the next. So we will talk about the inner orbital complex and outer orbital complex one by one. So first of all, your fluoride, chloride, bromide and iodide. These are weak field ligands. And the NiCO whole 4 and ZnNH3 whole 4 2 plus, they all form outer orbital complex. Now here your Ni is an exception because Ni has a configuration of what? It is having a total of how many electrons? 10 electrons, but still it shows a outer orbital complex formation. Now moving on to the examples. First of all, we will see the inner orbital complex which is NiCN4 2 minus. As I said earlier, so you will remove 2 electrons from the nickel to make it to +2 oxidation state. So it will have D8 configuration. Now due to the presence of a strong field ligand and the D8 configuration, it will pair up its electrons to form the dsp2 hybridization, and hence it will form square planar complex. Okay, any doubt in this part? See, it is quickly written here, and you will always see that the square planar complex have 8 electrons for the metal ions. Anyone who has a doubt in this? So you can comment your doubt in the comment section. So can you tell me what is the magnetic moment of the given complex? If this is your NiCN4 whole 2 minus is your complex, then what is the magnetic moment? Can you tell me? It's very easy, I guess. The formula is known to you. And also tell me that what will be the magnetic moment of NiCO whole 4? Yes, it will be 0. Very good, Shivam. So can you tell me what will be the magnetic moment of NiCO whole 4 if it is forming a outer orbital complex? So see, here your CO4 is present here, right? Means the ligand which is present is strong in nature, but still it is not forming a square planar complex. Got it? So what will be the obvious reason behind it? Because it is not having D10 configuration, sorry, D8 configuration, right? And that is the reason it is not forming a square planar complex. It is forming a tetrahedral due to outer orbital complex. Got it? So that is the thing I was explaining it to you. That remember, always D8 configuration is required. The presence of strong field ligand is not enough. So this CO is a strong field ligand, but still it is not forming a a square planar complex. Got it? So yes, the 0 will be the magnetic moment because all electrons are paired up, and hence it will be diamagnetic in nature. Now moving on. to the examples of outer orbital complex. So we will take COCl4 2 minus, right? So here it will be 2 minus. Now next, if it is 2 minus, that means the cobalt will be present in +2 oxidation state. So we will remove 2 electrons from the 4s. Next, there are 4 Cl ligands. So they will donate, each will donate a pair of electrons to the empty orbital, creating a sp3 hybridization where the S and P belongs to the 4th shell. Now, what about the number of unpaired electrons? It is obviously 3. So the formula for the magnetic moment is root under 3 into 3 plus 2. From there, you can also calculate the magnetic moment. Is it clear to you? So this will be COCl4 2 minus. Any doubt in this part? Anyone? So why are we getting here a outer orbital complex? Because chlorine is a weak field ligand and the weak field ligand are not capable of pairing up the electrons. And second thing that you can notice is that cobalt is not having D8 configuration in the oxidized state. It is having D7 configuration. Okay, so these two reasons is the reason for the formation of outer orbital complex. So this was all about the tetrahedral complex. Now before moving on to the octahedral, let me just write it here that what are paramagnetic substances. So they have unpaired electrons in their metal ion, whereas the diamagnetic substances have unpaired electrons in the metal ion. Okay, and the magnetic moment mu is calculated as root under n into n plus 1. So paramagnetic have unpaired electron and diamagnetic have no unpaired electron. Got it? It's very simple. One more important point, your magnetic moment has a unit of Bohr magnetron. So this Bm is representing the Bohr magnetron. After that, we will talk about the limitations of valence bond theory. So before introducing you to the crystal field theory, let me just make it clear that why it was important to develop the crystal field theory. First of all, the first limitation about this was a lot of assumptions. Okay, so it is basically coming from the valence bond theory, and you know that the valence bond theory has lot of assumptions like the orbitals will hybridize together and form a set of degenerate orbitals. They will be of equal energy and equal shape. So these are assumptions and they are very high in number. And the reason for assumption is not mentioned at all. Okay, assumptions are good, but the reason also should be mentioned here. But there are no assumptions in the valence bond theory. Next, it is only providing a qualitative nature. So it is not telling me exactly about that what is the identity of the ligand, whether it is a strong field ligand or a weak field ligand. It has no explanation regarding that. Got it? Second thing, we know that it shows a adsorption spectra, means it is showing colored ion formation. So no explanation was provided by the valence bond theory regarding the formation of colored ions. Next, it has no information about the magnetic properties as well. So the valence bond theory is not making clear that whether a given complex will be outer or inner. Okay, it is saying that thing on the basis of the results. It has no understanding from the start. So basically it is something which is experimental, and hence we cannot know that whether a given compound is outer orbital or inner orbital, and hence we cannot know the magnetic properties also, because that is based upon the fact that we should already know your complex nature, whether it is inner orbital or outer orbital. After that, it has no interpretation for thermodynamic or kinetic stability, that whether the given compound is stable or not, or it is reactive or not. Next, you can't predict the tetrahedral nature and the square planar complex. And lastly, we have no identification of the ligand in the formation of the compound and its properties, like your magnetic properties. Second, your colored complex formation, and third, your predictability of the tetrahedral or square planar complex formation. So these three things are where your valence bond theory has no further explanation. At this point, we have to introduce our crystal field theory. It's very simple. First of all, you have to understand that what happens in your crystal field theory. Now, unlike your valence bond theory, where we see the formation of your hybridized orbital on the basis of covalent interaction. Here we have ionic interaction, means the metal ion is taken as the positively charged species because it is present in some oxidized state, and your second thing, which is your ligand, they are taken as your negatively charged species because they have a pair of electrons. Now when they will approach each other, the d orbitals which were having similar energy, so they were known as degenerate orbital. You know it very well. 5 set of orbitals are possible for the d subshell: dxy, dyz, dxz, dx square minus y square, and dz square. So these 5 orbitals are considered to have equal energies, and they hence they are known as degenerate orbitals. But as soon as your ligands approach the d orbitals of your metal ion, your d orbitals are splitted. Okay, now this splitting is based upon the nature of the ligand, and we will study about them. So if I write it, your splitting of d orbital is simply the splitting of 5 d orbitals into 2 sets. So I am talking about here tetrahedral and octahedral only, due to the approach of the ligand, and this is known as the crystal field theory. Now the set of 5 orbitals which are having a similar energy, and hence they are known as degenerate, they are separated into 2 sets in the octahedral and tetrahedral complex. And why it is happening? It is happening due to the interaction of the negative field of the ligand and the positive field of the metal ion. Okay, so in this continuation, first we will see the splitting pattern of your octahedral entity. Now it is very important to remember the splitting pattern, that in what kind of 2 sets your degenerate d orbitals are splitted. So first of all, if I represent the splitting pattern, so what is splitting? What is splitting? So splitting is basically your one set of orbital is present at a certain energy, suppose. Now what is happening? As your ligand is approaching, your set of d orbitals, some part of it is going into higher energy and some part of it is going into the lower energy. So this splitting of your d orbitals into 2 different sets of energies is known as the splitting of d orbitals. So this is the idea behind it. It is not that your d orbital is getting torn apart. Got it? So basically they are going into 2 different sets of energy, and the difference between these 2 sets of energies is known as delta O. Okay, so you know it very well that for difference we use this delta, and since it is specific for your octahedral complex, we use the delta O as the subscript for octahedral. Okay, and this delta O is known as the crystal field splitting energy for the octahedral complex. Clear? So it's very easy to understand. Now next, if I tell about the rise of energy, then your 2 Eg orbitals, their energy is increased by 3 by 5 delta O. So the total energy is delta O, right? So this is, if this is your starting point, so 3 by 5 delta O is the increase in energy for the 2 set of Eg orbitals, and 2 by 5 delta O is the decrease in energy for 3 T2G orbital. Now this would be more clear with the help of your image. Okay, so this is your image. It is the starting point where all the metal d orbitals are present. Now slowly what will happen? Initially that is symmetrical in nature. Now the ligands are approaching. So initially all of them will be raised to a certain energy. So listen to it very carefully. It is very important to understand this phenomena. So first of all, the metal d orbitals, which are dx square minus y square, dz square, dxy, dxz and dyz, all of them are present in the same energy level. Now as the ligands approach, initially all of them are raised to some energy level, right? Still they have the same energy to this point, but as the proximity of your ligands is decreased, means they are coming more and more closer to the metal ion, then this 5 set orbitals are split into 2 parts. So this is for octahedral. So if this is the total delta O, then this part, which is 3 by 5 delta O, is the increasing amount of the Eg set orbitals, which is your dx square minus y square and dz square. So what are the orbitals that are going up in the energy? They are dx square minus y square and dz square. Whereas the remaining 3, which are dxz, dyz and dxz, they are going down by 2 by 5 delta O. So this is known as the barycenter. The beach energy, the middle energy, this is known as the barycenter, and the energy difference these two is delta O. Now from this point to the upper part it is 3 by 5 delta O, from this part to the lower part it is 2 by 5 delta O, and if you add both of them together it will be 0. Now there is a question, why dz square and dx square are more energetic than other. Now this thing basically depends upon the approach of ligand. In case of octahedral complex, so this is very peculiar, listen to it very carefully. Your octahedral complex has the approach of ligand along the axis. Okay, now what is along the axis? If you consider the shape, or if you consider the 5d orbitals, then 3 of them are between the axis, which are dxy, dyz and dxz. You can look at the diagram of them or the orbital picture of them. You will clearly see that in bit the lobes are present between the axis, whereas in the case of dx square minus y square and dz square, the lobes are present along the axis. Okay, as a result of this, since your ligands are approaching along the axis, there will be much more interaction, and hence their energy will be increased to a greater extent, because still the metal is present in positive charge, but they have electrons in their atom. And same can be said about the ligand, which is already having a lone pair. So due to the closer approach of the ligands which are coming along the axis, and the dx square minus y square or dz square which are present along the axis, there is a lot of repulsion, and hence they go higher in energy as compared to those which are present in between the axis. Okay, you can just quickly look at the diagram of these 5 orbitals. You will see the reason behind it. Is it clear to you? So the basic idea is that in octahedral complexes, ligand approaches along the axis, whereas in a tetrahedral complex, the ligand approaches between the axis. So in that case, this order will be reversed, because the repulsion will be faced more drastically by the dxy, dxz and dyz. Is it clear to you? Did you got my idea? Okay. Now, next, remember that these two set of orbitals are raised by 3 by 5 delta O, and these 3 sets of orbital are lowered by energy of 2 by 5 delta O, and this delta O is the stabilization energy. Now next, this delta O is the way we can compare the pairing energy, or we can know that whether a given ligand will show high spin complex or a low spin complex. So let me tell you to in the diagram here only. So suppose if your pairing energy is high, means the energy which is required to pair up 2 electrons, that energy is high, then what will happen? Your electron will go into the higher orbitals. Okay, so there are 2 energies which you have to compare. First one is the pairing energy, means the energy required to pair up 2 electrons, and the second type of energy is to go into this higher orbital, which is having representation as delta O. So if you have to bring electrons from here to here, you have to supply delta O energy. Now if delta O energy is less as compared to the pairing energy, then in that case your electron will go into the upper orbitals rather than getting paired up. And if the delta P energy is less, means the pairing energy is less, in that case the electron will get pair up rather than going into the higher energy. Okay, now just go back into the previous part. If it is getting paired up, if you means that if your pairing energy is less, then in that case your inner orbital complexes are formed. Okay, and if your delta O is less, means this splitting energy is less, then in that case the electron will go on to the higher orbital, and hence it will form outer orbital complex. Got it? So here you can clearly see that your crystal field stabilization theory is capable of telling you that whether a given complex will be inner or outer. So this is something which is known as quantitative data. In previous case we were getting only qualitative data and not a specific reason regarding it, and here we are getting the appropriate reason regarding it. So this can be written here also. So for high spin and low spin complexes, it all depends upon the role of your ligand field. If your pairing energy is higher, therefore your pairing will not take place and your electron will form the high spin complex. Okay, they will prefer to go into the higher orbital rather than getting paired up. If it is having a lower delta O, in that case in a lower delta, a lower p means a lower pairing energy. In that case, the electron, what it will do, it will get paired up rather than forming a higher spin complex. So in this case, inner orbital complex will be formed. Okay. So if I take it for the example, there are four electrons. Now three of them will be filled in the lower energy. There is a chance that the fourth electron can go into the upper energy, or it can get paired up with the electron that is already present in the lower energy. Suppose the delta O is higher, means the energy requirement to go in the higher state is higher as compared to getting paired up. So what it will do, it will get paired up, and hence all the electron will be in the lower level, which is known as T2G. Now one more important point here. What is T2G and EG? So T2G means triply generate, triply degenerate, means three orbitals having same energy, and EG means doubly degenerate, means two orbitals having same energy. Okay, so we have seen it in the case of octahedral complex, that out of the 5d orbitals, 3 are present in the lower state, and hence they are in a count of 3, and they all have the same energy, so they are known as triply degenerate. Whereas the two sets which are going up, they are in the count of 2 and they both have the same energy, so they are known as doubly degenerate. Next thing that you are seeing is your G. So this G is representing a G-red complex. Okay, so this is something we will learn in the higher classes. So I am keeping it to this part. And this G is only used in case of octahedral complex, because octahedral complex are G-red in nature. Okay, this is just for a way to remember it. So octahedral complex are G-red in nature, so we will use the term T2G. Whereas in tetrahedral complex, it is not G-red in nature, we will use T2. So G-red is G-E-R-A-D-E. So this is a terminology used in your symmetry. Okay, we will not talk about that now. Now next, moving on to the tetrahedral coordination complex. Okay. So this is your tetrahedral coordination complex. What can we say here? We can clearly see that the splitting pattern is reversed. Okay, means now the dx square minus y square and dz square, they are present as a lower set of orbitals. The same procedure is occurring here also. First of all, the d orbital is going from a lower energy to a higher energy, and then it is getting splitted into two parts. But the 3 by 5 which was present in the up part, now it is present in the down part, means the two orbitals are getting lowered by 3 by 5 delta t. So this t in the subscript is representing that your splitting energies for the tetrahedral complex, whereas the three set of orbitals are going into the higher energy, which is dxy, dyz and dxz. Here one more important thing that I said earlier, you won't see T2G, it is only T2 and E. Okay, no G here, because tetrahedral complexes are not G-red in nature. Okay, so this is the energy order. Clear? One more important thing, that for the same kinds of ligand, okay, suppose the metal ion is represented by A, okay, and the ligands are represented by X. In that case, suppose two kinds of compounds are formed or complexes are formed. One is tetrahedral, one is octahedral. Now for tetrahedral, the coordination number will be 4. So the complex will be AX4. Whereas for the octahedral, the coordination number will be 6. So the complex will be AX6. In these two complexes, the energy relation between the splitting part would be delta T is equals to 4 by 9 delta O. Means for the same metal ion and for the same ligands, but of different count because of the different coordination number, always the energy of octahedral splitting will be higher. And you can see here that delta T is 4 by 9th of the delta O, means it is smaller than the delta O. And the reason behind it is very clear. The reason is that your number of ligands is less, so the interaction is less, and hence the splitting energy is less. Now next, this tetrahedral complex will always be of low spin. Why? Because this energy is already very much lower. Got it? So the pairing energy will be always higher than the delta T, means the splitting energy. Got it? Therefore, rather than pairing it up, your electron will always go on to the higher energy state, and hence it will form the what? It will form the electrons in the higher orbital. Therefore, low spin is not observed or rarely observed in the case of tetrahedral. Got it? Next point, as a result of this less crystal field stabilization energy, and this can be clearly seen here. If you compare the splitting energy of the delta O and delta T, then delta T is very much less. It is 4 by 9. So as a result of this low tetrahedral energy, your pairing is not preferable, and hence it always form a high spin complex. Last point, the arrangement of ligand in the increasing order of field strength is known as spectrochemical series. Okay, so I will suggest to you that you can just go and check this spectrochemical series. We have already seen a part of it, so I'm not representing it here. So we have iodine, bromine, chlorine, bromine. They all the halides are your weak field ligands, whereas all the organic ligands such as carbonyl, cyanide, they all come under the strong field ligands. Okay. Now your ammonia that you have seen, that ammonia depends upon the metal ion. Okay, so nitrogen containing ligands, their ligand strength depend upon the nature of the metal ion. So if it is cobalt 3 plus, then in that case specifically you will see that all the complexes are inner orbital, okay, with ammonia. But if it is not cobalt 3 plus, if it is apart from that any 2 plus ion, bivalent ion, then it will be a, your NH3 will be a weak field ligand. So these are the two cases of your NH3. Lastly, one more important point, you can write it in your notebook if you want. Yes, it is important to remember the series. It is very, very important. So one more important point you should remember, that all the metals ions of the 4D and 5D series. Okay, so we have three series, 3D, 4D and 5D. All the metal ions of the 4D and 5D series will form a lower inner orbital complex. Okay, means they will always form a lower spin complex. Is it clear to you? Any doubt in this part? So I have told you three important points. Write it down. I am telling you it again. First of all the fluorine, chlorine, bromine, iodine, including water, okay, and SCN and S2 minus, all of them are weak field ligands. Okay, this is the first set. Second, all the organic ligands such as cyanide, carbonyl, they are strong field ligands. Now, for NH3, we have certain important criteria. What is that criteria? If NH3 is forming bonds with a cobalt 3 plus, then it will form a strong field ligand. Your ammonia will act as a strong field ligand. Or else, in every case, it will act as a weak field ligand. And the last point, what is that last point? That your 4D and 5D series metal ions will always form a what? Inner orbital complex. Means all the ligand will act as a strong field ligand for 4D and 5D series metals. So you can take any example of that. It can be tungsten, it can be molybdenum, it can be platinum, it can be palladium. For each of them, your all ligands will act as a strong field ligand. Got it? I hope this part is clear to you. And from this also a question is asked. For example, the Wilkinson catalyst. Okay, there it was asked that what kind of complex is Wilkinson catalyst? It is a lower spin complex or a high spin complex. So first of all, your Wilkinson catalyst is containing rhodium as the metal, and rhodium belongs to the 4D and 5D series. To one of them, I think it is 5D series, right? And I said it earlier that for every 4D and 5D series element, each time your complex is formed, it is a inner orbital complex. Means every ligand will act as a strong field ligand. Now, if this part is clear to you, can we move on to the next? Anyone who has a doubt in it? So I am leaving it to you. You have to just learn the spectrochemical series from the NCRT. It is given there, and it's very, very important for you. And the points that I have mentioned, they are also important. Just write it down. It will be handful in the upcoming questions as well. Any doubt in this part? Is it clear to all of you? Anyone who has a doubt? So please comment it here so that I can get an idea if you are getting my point or not. If you don't have a doubt, just send that okay. It's all good. Anyone who has a doubt till this part? So is it clear to all of you? Okay, so let us move forward. Now, next, regarding the color in your coordination compound. Okay, so the basic and the most important for you is the DD transition. So, we have talked a lot about it. I will just put some important points regarding it. So, just listen to it very carefully. So, first of all, in your complexes, your d orbital is split into two parts, which is T2G and EG, and they have different sets of energy. So, this is specifically for your octahedral complex. Now, as a result of this, your electrons are excited from a lower energy level to a higher energy level. Okay, so that occurs in the case of D1 to D9. Now, why it is not possible for D0 and D10? Because for D0, in the case of D0, there are no electrons present, so transition is not at that possible. And in the case of D10, all the orbitals are fully filled. Okay, so there is no chance of transition, means there is no space for the lower electron to go into the higher one because all the space is occupied. So in these cases, the DD transition is not absorbed at all. So it is only observed if they are capable of showing DD transition. And what is the reason behind it? The reason is the charge transfer spectra. Okay, so we have talked about an example regarding a complex that shows a charge transfer spectra. Now, two kinds of charge transfer spectras are possible. Okay, so write it down. I've not written it here. It may be handy for upcoming slides. So the first thing is that it is known as ligand to metal charge transfer, and the second one is metal to ligand charge transfer. Okay, so here the charge which is transferred is your electron, and you know that your charge which is your electron will be attracted to your positive charge. Clear? So the first one is ligand to metal charge transfer. You can simply abbreviate it as LMCT, and metal to ligand charge transfer, where it can be abbreviated as MLCT. Now for ligand to metal charge transfer, your metal should be present in a very high oxidation state. Okay, for example, if I take the case of KMnO4 minus, just search for the color of KMnO4 minus. It is purple in color and it has an intense color. Okay, since it is not showing and it is not showing the DD transition also, because no electrons are present in the d orbital. In the manganese, if it is present in the +7 oxidation state, means all the electrons are being removed, but still it is showing color. So there the role of ligand to metal charge transfer take place. So basically, since your manganese is present in a very higher oxidation state, it is containing a charge of +7. As a result of this, it will attract the electrons from the ligand. Okay, and as a result of this, it is showing the color. So the first point is that for your ligand to metal charge transfer showing, your ions should be present in highest oxidation state, like +5, +7, +6 for osmium and all. And opposite is true for the metal to ligand charge transfer, which is MLCT. In that case, your metal is transferring the electron. So your metal should be present in a lower oxidation state, like +2 or +1 or 0. Okay, so this is something which we can note it down, and it may come handy for your questions, because it may help you to predict whether a given compound is colored or not, although you don't know about the DD transition or there is no DD transition. Now, next we have stability of complex ions. So this is something which is not that much important, but still there are some instances where you will see questions where you have to compare the stability of the complexes. Okay, so first of all, if you look upon this formula, it clearly shows a very simple phenomena where your metal is attached to n number of ligands to form the MLN. Okay, so if n number of ligands are attached, it will form MLN. Now for each step, there would be a stability constant, which is K1, K2, K3, and it can be for nth number of ligand. Overall, this is known as the stability constant, or beta n. Okay, now K1 and K2 and K3, they are stepwise formation constant. For each step, you can write the equilibrium constant K. Suppose the first ligand is added, means M plus L gives us ML. So for that, it is K1. Then for ML plus L, it will give you ML2, which is K2. Then ML2 plus L, then ML3. Similarly, you can go on to ML6 for octahedral and ML4 for tetrahedral. So for each of the step, there will be a stepwise constant, and if you multiply them together, you will obviously get the overall stability constant. And the reverse of it means 1 by k or 1 by beta n is known as the instability constant. Now, what are the factors on which your stability depends? So, first of all, if your metal has a higher charge, then in that case, your metal will form a very stable complex, because we know it from the CFSC, overall interaction of the ligand and the metal is electrostatic. Now, for strong electrostatic interaction, the charge magnitude is directly proportional to the interaction, because you know it, force is directly proportional to the product of the charge. So basically, if charge is higher on the metal ion, it will obviously form a strong metal complex, okay, or a stable metal complex. Next, next is your stability coming from the ligand. So we have seen that the magnitude of splitting depends upon the ligand. So strong field ligands form a higher splitting. Okay, so for example, if we take NH3, 6 NH3 ligands and 6 carbonyl ligands, then the carbonyl ligands are stronger. Therefore, they will result in a higher splitting and the delta O will be larger as compared to the NH3 or your fluoride splitting. Got it? Now, greater is the stabilization energy, greater is your stability. Okay, so it is directly proportional. Got it? Means your strong field ligands are capable of showing higher stabilization energy or higher CFSC value, and hence they form stable compound. So 2 points you should remember. First point is that your metal charge, if it is higher, then your complex will be stable, and if second point, if your ligand is strong, then in that case your complex will be stable. But the predominant factor is your charge or metal ion. So it is the primary factor. If the charge is same, then you will look upon the ligands. If the charge is higher, then you will directly conclude it from the charge itself. You will not go on to the ligand part for comparing the stability of the complex. I hope this part is clear to you. Now, moving on further in the stability of the complex, next is the chelation. Okay, so we have been taught about this chelate compounds, where your polydentate ligand or your bidentate ligand are forming ring along with the metal complex. For example, if you take the case of complex formation with the help of oxalato ion, in that case we see the formation of your ring. So if six ligands are present, and in place of that, if I put a hexadentate ligand where multiple cycles are formed, so that would be more stable. Okay, means if there is a possibility for the formation of chelation, then your chelate factor is much more predominant than the unidentate ligand. Next, the same point is written here. So in case of multidentate ligand, if the chain is formed in multiple times, so suppose if one is forming the chelation, other one is forming the unidentate, then the chelation will be stable. Now suppose both of them are forming chelate, so what would be seen in that case? In that case, we will look upon the steric strain. Means you know that the 5-membered ring are stronger, so they will form a stronger complex or a stable complex as compared to the one which forms a 3-membered ring. Okay, so in that case, you will compare the ring strain. Now, lastly, there is a small formula to calculate the stability of a complex, which is known as effective atomic number. Now, how can you calculate it? It's very simple. So the formula is given as atomic number of the metal plus minus the valency, means the number of electrons which is removed or the number of electrons which is added. Of course, it will be removed. 2 multiplied by Cn, which is the coordination number, because each ligand contributes 2 electron. Therefore for 6 coordination number, 12 electrons will be there. So if this count you are getting upon calculation of EAN, if it is close to a noble gas configuration like 18 or 36, in that case your compound will be stable. So you can also compare the stability using this thing if all the rules are failed. So first of all, you will look upon the metal ion charge. Second, you will look upon the ligand, whether it is strong or weak. But if it is forming a chelation, then that would be more stable. Got it? So in that case, your spectrochemical series will be kept aside. Now suppose two are forming the ring, then what you will do? In that case, you will look upon the steric factor, whether the ring that is formed is stable or not, if there is steric strain or not. And lastly, if all the rule fails, you will use this formula to calculate the EAN, known as effective atomic number. Got it? Now, we will move on to the application of coordination compound. So, what is application? So, first application is that it is seen generally that with the presence of the calcium 2 plus and the magnesium 2 plus, what happens? There is hardness of water, due to which it is difficult to use it in daily purpose. Now, how do we remove it? It's very simple. We do the titration of your water with the Na2EDTA. Since the charge is higher in case of calcium, so rather than chelating with the one sodium, it chelates with the calcium because that is a stable complex. See, here is a direct application of that concept. What is the reason of removal of this Na and catching of this Ca2 plus? The greater charge. So, if you dissolve Na2EDTA into the water, it will quickly substitute its Na with the calcium 2 plus because of the higher charge on the metal ion, and same can be said about the magnesium, and hence this will be removed along with that. Okay, so how hardness of water is treated with the help of EDTA. Now next, some important extraction processes are also done with the help of silver for the silver and gold using that same complex formation. After that, we have something known as the Mons process. How it is done? So, what we do is we introduce the ligand into the impure nickel sample. So, what will the carbonyl do? The carbonyl will form the complex with the nickel like NiCO whole 4, and then we can remove this NiCO whole 4, and from that we can get our nickel. Okay, so suppose there is a large amount of impurity present. Now you are only taking out the nickel using the carbonyl, then you can further decompose it. So it is decomposed upon heating and releases our required nickel metal. So this can also be used in the purification process. So we talked about this, the Wilkinson catalyst. It is used for the hydrogenation of alkenes, means conversion of alkenes to alkanes. So in this case, the rhodium, since it is a 5D series element, therefore it will always form a what? Low spin complex because of its lower energy. Okay, no matter which ligand we are taking, each ligand will act as a strong field ligand for the rhodium. Got it? Lastly, this can also be used for the removal of toxic materials. For example, copper and iron, if the amount of copper and iron become excess than the required amount, then they are removed with the help of D-penicillamine, okay, or D-ceferoxime. In both of these cases, what will happen? Your ligands will chelate with the copper and iron, and further they can be removed. In all of the application that you are seeing, the principle is same. The ligand is applied onto the required given metal and they form complexes with the metal, and further it is removed, and hence the sample is pured. Got it? Last topic, which is known as bonding in metal carbonyls. Now this is very important. Questions are asked from this point in multiple cases. Now what is the meaning of this? So metal carbonyls are coordination compound in which your carbon monoxide acts as a ligand. So carbon monoxide, it is a neutral ligand. Okay, remember, note it down. Carbon monoxide is a neutral ligand, and they form very strong bond through synergic interaction. Now what is synergic interaction? You must have seen in your phone sync. Okay, there is a option known as sync. If you sync, there are multiple syncing. You must have seen that your contacts are synced with your Google account. So that same syncing is shown here by the carbonyl. Let's see how. So here is a diagram. You know that from the crystal field stabilization energy concept that your ligand is donating electron to the metal. So that is something which is commonly known to you. Now a next phenomena is seen in the case of carbonyl. What is that phenomena? So carbonyl are capable of accepting electrons also. So they do not only donate it to the metal, they also accept it from the metal. Now initially there was a single bond using 2 electrons. Now there are multiple bonds. You can see here that the electrons are given into the pi star of the carbonyl. As a result of this, they form a synergistic effect. So here it is kind of synced with each other. So it is not attached in a single fashion, rather than it is attached in multiple fashion. Now here are some important points you can remember about this synergic effect. First is there is a sigma donation from the carbonyl to the metal. So carbonyl is donating its electrons onto the metal. First of all, first point. Then as the electrons are donated onto the metal ion, but the metal ion is present in the zero oxidation state. I said it earlier that carbonyl has zero charge. As a result of this, the resulting complex is also having metal ion in the zero charge state. Sorry, metal in the zero charge state. Why? Because the complex needs to be neutral. If one is neutral, the other has to be neutral. As a result of this, your charge on the metal is increased. Now what it will do? Due to this extra electron density, it will donate it back to the carbonyl, which is known as pi back bonding. Okay. So what is the definition of pi back bonding? The donation of the metal electrons from the pi orbital to the empty pi star orbital of the carbonyl. Write it down. The donation of electrons from the pi orbital of the metal to the empty pi star orbital of the carbonyl is known as pi back bonding. Now here, from here, questions are asked directly in a statemental way. You must have seen a question like this. So what is happening here actually? So first your ligand is donating your metal through sigma donation, and the metal is donating its electron back to the ligand by pi back donation, and this creates a synergic effect. And this synergic effect is mostly shown by, and according to your syllabus, it is mostly important regarding your carbonyl. Okay. Now multiple of ligands are possible which are capable of showing this kind of synergic effect, but you have to only know about this carbonyl. Okay, so this was all about the theory part. Now we will try to do some questions on it. So just wait for a while. Let me show you some questions. So here is the first question. The number of geometrical isomers of CO, NO2 whole thrice, NH3 whole thrice is. So four options are given here: 2, 4, 3 and 0. Okay, you have to find the number of geometrical isomers. So your time to solve this question starts now. Just see what will be the correct answer. So it is a complex which is consisting two types of ligand present in a set of three, and this is the octahedral complex. Now you have to see that what are the possible geometrical isomers for the given complex. So just write your answer here in the comment section. What will be the correct answer? Anyone, can you tell me? So it's very simple. Let me give you a hint for it. You have talked about this facial and meridional. Okay, yeah, so I'm seeing answer 2. Anyone else? What will be the correct answer for this question? It's very simple. Option number A. Anyone else who can give the answer? Okay, two answers are already here. So, moving on to the answer. Yes, the correct answer would be 2. It's very simple. So, your complex of that is of the type Ma3B3, and they are capable of showing facial and meridional isomers. Now, this can be seen here. Now, how will you remember that a given isomer is facial or meridional? So, there is a small hint for you. What is that hint? Always consider the angle. That what is the angle? If there is 180-degree angle between identical ligands, then in that case it will be meridional always. For example, if we take this meridional complex, here you can see that these two NO2 which are identical is present at an angle of 180 degree. So you will also always consider them as meridional or trans. But if you consider this structure or this geometrical isomer, you won't see two identical ligand present an angle of 180 degrees. See, the NO2 and NO2 angle is 90 here and again 90 here. There is not even a single 180-degree angle between two identical ligands, and hence it is an example of facial. So from this you can identify the facial and meridional, and there can be a question to identify the facial and meridional in your examination. Okay, so you can use this trick quickly to solve the question. Next question: the complex PTPY NH3BrCl will have how many geometrical isomers? So we have talked about this in the previous class, I guess. So you have to tell it for a complex of M, A, B, C, D type. But before that, you have to also know that whether this complex is tetrahedral or square planar. So that is your uh, work to do. Okay, so this is very important, and we have talked a lot about this, that how to identify that whether a given one is tetrahedral or square planar. So first give me the answer that whether this complex will be tetrahedral or square planar, because both have a coordination number of 4. How you will do it? Remember, you have to identify the D8, whether it is D8 or not. And remember that all the ligands for 4D and 5D series is strong field ligand. So first of all, tell me that why the given complex will form 3. Means if you are telling it as 3, that means you know that it is a square planar complex. So is it true? Will it form a square planar complex? Just think about it. And what is the reason? So the two reasons that you can probably think are what? Is it having a D8 configuration, your PT? It is present in the +2 oxidation state, because your Py, which is your pyridine, and your NH3, which is your ammonia, both are neutral in nature. So Br and Cl are to be considered, and Br and Cl are having 1 negative charge. Yes, it is having a D8 configuration. So see how it is useful here. If you are not able to know that whether a given complex is tetrahedral or square planar, then you won't be able to solve the question, because if it is tetrahedral, suppose you assume that if this is a tetrahedral, then tetrahedral complexes never show geometrical isomer. So the answer would be 0, and you will be wrong at that moment only. So first of all, you have to identify that thing. So here it is D8 configuration, and for the 4D and 5D. So here second concept is used, is your formation of strong field ligand for 4D and 5D. So always your 4D and 5D elements have strong field ligand. Okay. So from these two concepts, you may be very clear that the given complex is square planar in nature. Next, since it is a square planar, you know it very well. So you can clearly see that 3 geometrical isomers are possible here. Is it clear? So did you get the point of knowing that your PT, PY, NH3, BrCl is a square planar? So that is something which is more important than knowing the number of geometrical isomers. Okay. So any doubt in this? Are you able to identify coordination number of 4 as your tetrahedral or your square planar? So if you have a doubt, you can ask it right now. Yes. So I hope it is clear to all of you. Now, moving on to the next question. So the complex would be, okay, so answer. So this, it will be 3 obviously, because it is a square planar complex of type M, A, B, C, D. And hence 3 geometrical isomers possible are PT in the middle, PY. So keep the one ligand as constant and try to rotate the other 3, and you will get your 3. So first we have kept PY and BR at the 180 degree, then PY and NH3 at the 180 degree, and PY and Cl at the 180 degree. So these are the 3 possibilities. So it is a mnemonic to just draw it very quickly. You have to only look upon the 180 degrees. So there must be a 180 degree with each of them. So you can take PY as the constant also, or NH3 or BR or Cl. It depends upon you. Then you have to just change the other part. So PY BR, PY NH3 and PY Cl, and then you will ultimately get your 3 geometrical isomers. Next question. Again, This question is from the number of geometrical isomer that can exist for the square planar complex, which is PTCl PyNH3 NH2OH. So it is a similar kind of question. We will not discuss much about it. Since it is square planar complex, it is already mentioned, and you know it also that your D8 configuration with strong field ligands, since it is at 4D and 5D, so all ligand will be strong for it. Therefore, it will form a square planar complex. So although this thing is not mentioned here, you can easily tell that the correct answer would be 3. Yes. So the answer would be 3. And what are those three groups? What are those three geometrical isomers? So again, you will use that same phenomena. You will keep here one of them constant and try to rotate the other three. So one is NH2OH, then NH3, and then Cl. And hence you will get your three geometrical isomers. So try to draw also. If you are doing it for your practice, try to draw also the geometrical isomers. Next question. Consider the following reaction and statements. The question says that your CONH3 whole 4 Br2 plus Br minus is reacting together to form CONH3 whole thrice Br3 plus NH3. Now you have to tell that the two isomers are produced if the reactant complex ion is cis isomer. Two isomers are produced if the reactant complex is a trans isomer. Only one isomer is produced if the reactant complex is a trans isomer. Only one isomer is produced if the reactant complex one is a cis isomer. Now this one is a typical question from the reactions of your coordination compound. Okay. Now this is not generally asked in your exams. In the recent days I have seen it. So if you are not able to solve it, no worries. If you are getting the answer, you can just comment it here. Options are A 1 and 2, B 1 and 3, C 3 and 4, and D 2 and 4. So what will be the answer? Okay. So moving on to the correct answer, it will be 1 and 3, which is option number B. So basically, if the reaction is cis isomer, then the following reaction takes place. So this is your Br minus, okay, and this is a cis isomer because your Br are present at the same 90 degree. Okay, if they are present at 180 degree, then it would be a trans one. Now next, what will happen? Your Br will come here and substitute this NH3. Okay, and that will result in two kind of isomers. The first one is the facial one, and the second one is the meridional one. Next, hence we can say that two isomers are produced. After that, what about the third one? So if the reactant is trans isomer, then the following reaction is taking place. See, here we have taken the trans one. One Br is present at the up part, one at the down part. Means the corresponding angle is 180 degree. Now, if you have to remove the NH3, what will happen? This NH3 will be removed and Br will be introduced here. So in this case, we are getting a meridional. So we are not getting facial and meridional both. Therefore, the correct answer would be 1 and 3. So if you are not able to solve it, no worries. These questions are not asked in your recent exams. So these were some questions from the reactions of coordination complex. So our last question of today's discussion, which one of the following complex shows optical isomerism? First one, cis COEN whole twice Cl2Cl. Second, trans COEN whole twice Cl2Cl. Third one, CONH3 whole 4 Cl2Cl. And last one, CONH3 whole thrice Cl3. So for this, you have to first of all draw the shape, and then you have to find the plane of symmetry. If you are getting a plane of symmetry, it will not show optical isomer. If it is not showing a plane of symmetry, then it will show optical isomer. Okay. So just try it by yourself and see whether your given complex is optical or not out of the 4 options. So your time starts now. So I am giving you 2 minutes to solve it. It's very simple. Simply you have to draw the diagram and look for the plane of symmetry. A plane that cuts the molecule into 2 equal halves. So that is something which is known as plane of symmetry. For example, if you take a square, if you dissect it in the between, you will get 2 equal halves. But if you take your hand and draw a line in the middle, you will see that the left and right part are different. Okay, so that is something which is not representing a plane of symmetry. So what will be the answer for this question? Can you tell me, anyone? It's very simple. Just quickly draw the diagrams of the four given structures. Remember, this is En, which is ethylene diamine, and it is a bidentate ligand where two CH2 are attached to each other and two NH2 are present on the terminal side of the CH2. That is something which is known as ethylene diamine, means two amines attached with the help of a ethylene set. Anyone who got the answer? What will be the answer for this question? What will be the answer for this question? Can you tell me? So just try to draw the diagram for each of them and see that if there is a presence of plane of symmetry or not. Okay. So moving on to the correct answer, it will be option number A, which is COEN whole twice Cl2 Cl. So let us see the solution. So this given complex is of the type MAA2B2. So this AA is representing a bidentate ligand where both the donor sites are same or the ligand is symmetrical in nature, and B is representing two unidentate ligand. So this is your cis one and this is your trans one. So for the trans one, if you want, you can cut it in the middle and you will get two equal halves. But if you do the same for this one, you won't get equal halves. Try to dissect it in multiple ways. You can bisect it diagonally, or you can bisect it in the middle. In each of the case, you will not get two equal halves. As a result of it, this form of your COEN whole twice Cl2Cl, which is cis, is your optically inactive complex. What about the other two? So this is your CONH3 whole 4 Cl2. So this is the trans one. Now the trans one is obviously what? Symmetrical. You can cut it from the middle. And same can be said about the cis one also. So this is the cis one. If you want, you can just cut it along the plane. Okay, so just cut it along the plane. So your NH3 molecule will be bisected into two halves. Similarly, this one, and this one, and this NH3 and NH3 will be mirror image of each other. So just imagine it. You are cutting like it in this middle. Okay, you are not cutting it diagonally or bisecting it in the like this. You are bisecting it along the plane of the four molecules. Therefore, you are getting two same things on both parts. And same can be said about the trans. Lastly, we have this CONH3 whole thrice Cl3. You can see both the facial and meridonial. So this one is also optically inactive because it can be cut down into two halves. Okay, and similarly your meridonial also can be cut down into two halves. So this one I am leaving it to you. Just try to cut it into two halves and you will clearly see that the two isomers are optically inactive. So this was all for today's class. Thank you for joining the session. I hope you enjoyed it.
Hello students, welcome to 40 days crash course. Today is day 26. So in this lecture we will discuss inverse trigonometric functions. So as you know, first of all we will discuss theory part and then we will discuss question part. Okay? This is our disclaimer. Wait a minute. So see here, first trend analysis. So first we will analyze last 5 years questions. Okay? So in this chapter at least one question you will get, okay, and the chapter weightage is 2.15 percentage. And then see yearly question distribution. In 2024, one question asked based on properties of inverse trigonometric functions, and here concept covered tan inverse x plus tan inverse y equal to tan inverse of x plus y divided by 1 minus xy, and the difficulty level was average. In 2023, one question asked, and that question based on range of trigonometric function, and concept covered range of sine inverse of x, this is equal to close interval minus pi by 2 comma pi by 2, and the difficulty level was easy. In 2022, one question asked, and that question based on properties of trigonometric function, and here concept cover tan inverse x plus tan inverse y equal to tan inverse of x plus y divided by 1 minus xy, and the difficulty level was average. Then you can see in 2021, in 2020, and in 2019, in each year one question asked, and that question based on properties of trigonometric functions, range of trigonometric function, and properties of trigonometric function. Okay, and the difficulty level was easy, difficult, average. So from this chapter, question asked, and that question difficulty level was of that question easy, average, and difficult. Okay, now we will discuss which topic we will cover in this lecture. Okay, so first we will discuss inverse trigonometric functions. After that, we will discuss some properties of inverse trigonometric functions, and finally we will discuss some practice questions one inverse trigonometric functions. Okay, so are you ready to start? So I hope you are well ready, okay, and you are with your notebooks and pens. So let's get started. So first we will discuss inverse trigonometric function. Okay, so trigonometric functions you will know, like sine x function, cos x function, tan x function, sec x function, cosec x function, cot x function. Okay, six basic trigonometric functions you will know. So trigonometric functions are not 1 1 and 1 2, okay, on their natural domains and ranges. Okay, so their inverse do not exist in the whole domain. So if we see whole domain of any trigonometric functions, so that trigonometric functions are not 1 1 and 1 2 on their natural domains and ranges. Okay, for example, sin x function. Sin x function, is it 1 1 and 1 2 in its domain? Everyone write your answer, yes or no. Is sin x function 1 1 and 1 2 in whole domain? Sin x function is which type of function? Sin x function is periodic function. Okay, so sin x function is not 1 1 and 1 2 in the whole domain. Okay, so we restrict their domain and range, and then their inverse may exist. Okay, so if we have any trigonometric function, and that case for existing the inverse of that function, we have to restrict their domain and range. Okay, Suppose you have y equal to f of x is equal to sin x. Okay, so then its inverse will be written as x equal to sin inverse y. So x equal to sin inverse y when you have y equal to f of x equal to sin x. So now note some points. So first you have to note here sin inverse y. This is not equal to sin y whole inverse. Okay, they are different. Sin inverse y is not equal to sin of 1 by y. Okay, so sin of y whole to the power minus 1. This is actually 1 by sin y. Okay, and 1 by sin y is not equal to sin inverse of y. Okay, and you also have to note sin inverse y is not equal to sin of 1 by y. Clear? Now, the value of an inverse trigonometric functions which lies in its principal value branch. Okay, so this is called principal value of that inverse trigonometric function. Okay, so first of all, we have seen here when uh, if we have any trigonometric functions, then that function is not 1 1 and 1 2, but for existing their inverses we have to restrict their domain and range. Okay, and then we have seen here some important note like sin inverse y is not equal to sin y whole inverse, and sin inverse y is not equal to sin of 1 by y. Clear? I hope you will understand. So now moving to the next. So now we will see domain and range of inverse trigonometric functions. So see this table. In this table we have inverse trigonometric function and their domain and range. Okay, basically here we have given range in principal value branch. Okay, so if we have the inverse trigonometric function sin inverse x, so sin inverse x, for sin inverse x the domain is close interval minus 1 comma 1. Okay, so in close interval minus 1 comma 1 sin inverse x function is 1 1 and 1 2. Okay, so this is existing. Okay, this is exist. So and the range of sin inverse x is close interval minus pi by 2 comma pi by 2. Then see for cos inverse x, domain of cos inverse x is close interval minus 1 comma 1 and the range of cos inverse x is close interval 0 to pi. Okay, then for tan inverse x, domain is set of real numbers. Okay, and the range is close interval minus pi by 2 to pi by 2. Then for cot inverse x, the domain is set of real numbers and the range is open interval 0 to pi. Okay, then for sec inverse x, the domain is set of real numbers minus open interval minus 1 comma 1. Okay, so in open interval minus 1 comma 1, sec inverse function is not 1 1 and 1 2. Okay, so inverse of sec x function does not exist. So for that we restrict domain. Okay, and here we have taken domain of sec inverse x. This is equal to set of real numbers minus open interval minus 1 comma 1. Okay, and the then we have range of sec inverse x is close interval 0 to pi minus singleton set pi by 2. Then see for cosec inverse x, so the domain of cosec inverse x is set of real numbers minus open interval minus 1 comma 1 and the range of cosec inverse x is close interval minus pi by 2 to pi by 2 minus singleton set 0. Okay, so you should keep in your mind the domain and range of these inverse trigonometric functions. Okay, so you have to memorize domain of sin inverse x and range of sin inverse x. You have to memorize domain of cos inverse x and range of cos inverse x. Okay, and similarly you have to memorize for tan inverse x, cot inverse x, sec inverse x and cosec inverse x. Okay, so I hope you will understand. Okay, and I know you will know, okay, the domain and range of these inverse trigonometric function. Okay, now moving to the next. Now we will see some properties of inverse trigonometric functions. Okay, so there are some important properties of inverse trigonometric functions that now we will discuss. So first property is sine inverse x plus cos inverse x. This is equal to pi by 2. Okay, and here minus 1 less than equal to x less than equal to 1. So you should keep in your mind this property we frequently use to solve many problems. One, inverse trigonometric function. Okay, then next see tan inverse x plus cot inverse x. This is equal to pi by 2, and here x belongs in set of real numbers. Okay, then sec inverse x plus cosec inverse x. This is equal to pi by 2 when x is less than equal to minus 1 or x is greater than equal to 1. Okay, that case sec inverse x plus cosec inverse x, this is equal to pi by 2. So you have to memorize sine inverse x plus cos inverse x, this is equal to pi by 2. Tan inverse x plus cot inverse x is equal to pi by 2, and sec inverse x plus cosec inverse x equal to pi by 2. Okay, and that you have to also keep in your mind this restriction of x. Okay, so for sine inverse x plus cos inverse x equal to pi by 2, here minus 1 less than equal to x less than equal to 1. For tan inverse x plus cot inverse x equal to pi by 2, here x belongs in set of real numbers. For sec inverse x plus cosec inverse x equal to pi by 2, here x is less than equal to minus 1 or x is greater than equal to 1. Okay, now see another property of inverse trigonometric function, that is sine inverse of minus x. This is equal to minus of sine inverse x. Okay, so here minus 1 less than equal to x less than equal to 1. So you will know about odd function. Okay, so if the function f of x we have, so f of x is called odd function if f of minus x, this is equal to minus f of x. Okay, so in this case you can see if we take f of x as sine inverse of minus x. Okay, so here f of minus x is sine inverse of minus x. So here you can write this is as minus f of x, that is minus sine inverse x. Okay, so sine inverse of minus x, this is equal to minus sine inverse x. Here we are taking f of x as sine inverse x. Okay, and then we check f of minus x, this is equal to minus f of x. So sine inverse function is odd function. Okay, that's why sine inverse of minus x, this is equal to minus sine inverse x. Here minus 1 less than equal to x less than equal to 1. Clear? Then see cos inverse of minus x. Cos inverse of minus x, this is equal to pi minus cos inverse x. Okay, here minus 1 less than equal to x less than equal to 1. Then tan inverse of minus x, this is equal to minus tan inverse x. Here minus infinity less than equal to infinity, less than equal to x less than equal to infinity. Okay, so x lies between minus infinity to infinity. So tan inverse of minus x, this is equal to minus tan inverse x. Yes, hello. Then see here cot inverse of minus x, this is equal to pi minus cot inverse x. Okay, here minus infinity less than x less than infinity. Then see sec inverse of minus x, this is equal to pi minus sec inverse x. Here x is less than equal to minus 1 or x is greater than equal to 1. Then cosec inverse of minus x, this is equal to minus cosec inverse x. Here x is less than equal to minus 1 or x is greater than equal to 1. Okay, so just recall these properties of inverse trigonometric functions. These are very important properties, so you should keep in your mind these properties. Okay, now moving to the next. Here the another property, that is sine inverse of sine x. This is periodic function, and what is the period of this function? The period of this function is 2 pi. Okay, sine inverse of 2x, sine inverse of sine x, this is a periodic function with period 2 pi. Now how can we express sine inverse of sine x? Okay, so when you have interval minus pi by 2 to pi by 2, when x lies in interval minus pi by 2 to pi by 2, then sine inverse of sine x, this is equal to x. When x belongs in closed interval pi by 2 to 3 pi by 2, then sine inverse of sine x, this is equal to pi minus x. When x belongs in closed interval 3 pi by 2 to 5 pi by 2, then sine inverse of sine x is x minus 2 pi. Okay, when x belongs in closed interval 5 pi by 2 to 7 pi by 2, then sine inverse of sine x, this is equal to 3 pi minus x. Okay, so you have to you have to keep in your mind these ranges. Okay, so when x lies in minus pi by 2 to pi by 2, then sine inverse of sine x is x. Okay, and similarly when x belongs in closed interval pi by 2 to 3 pi by 2, then this is pi minus x. When 3 pi by 2 to 5 pi by 2, then pi x minus 2 pi. When 5 pi by 2 to 7 pi by 2, then this is 3 pi by 3 pi minus x. Okay, understand? Then see another property, that is cos inverse of cos x. Okay, cos inverse of cos x is a periodic function with period 2 pi. Okay, now see cos inverse of cos x. This is equal to x when x belongs in closed interval 0 to pi. Cos inverse of cos x is equal to 2 pi minus x when x belongs in closed interval pi to 2 pi. Okay, when x belongs in 2 pi to 3 pi, then cos inverse of cos x is equal to x minus 2 pi. When x belongs in closed interval 3 pi to 4 pi, then cos inverse of cos x is equal to 4 pi minus x. Okay, so you have to first write the uh, interval. Okay, 0 to pi, pi to 2 pi, then 2 pi to 3 pi, and then 3 pi to 4 pi. Okay, so in closed interval 0 to pi, cos inverse of cos x is x. In closed interval pi to 2 pi, cos inverse of cos x is 2 pi minus x. In closed interval 2 pi to 3 pi, cos inverse of cos x is x minus 2 pi. Okay, in closed interval 3 pi to 4 pi, cos inverse of cos x is 4 pi minus x. Okay, this is how you can remember. Then tan inverse of tan x is a periodic function with period pi. And see here, tan inverse of tan x, this is equal to x when x belongs in interval minus pi by 2 to pi by 2. Okay, so first write the interval where x lies. So first divide minus pi by 2 to pi by 2, then pi by 2 to 3 pi by 2, then 3 pi by 2 to 5 pi by 2, then 5 pi by 2 to 7 pi by 2. Okay, then write tan inverse of tan x. So tan inverse of tan x, this is equal to x when x belongs in closed interval minus pi by 2 to pi by 2. Okay, and tan inverse of tan x, this is equal to x minus pi when x belongs in closed interval pi by 2 to 3 pi by 2. When x belongs in 3 pi by 2 to 5 pi by 2, then tan inverse of tan x is x minus 2 pi. Okay, and tan inverse of tan x is equal to x minus 3 pi when x belongs in closed interval 5 pi by 2 to 7 pi by 2. Okay, so these are some important properties of inverse trigonometric functions. So you should keep in your mind these properties also. Okay, now moving to the next. Now see cot inverse of cot x. This is also a periodic function with period pi. Now see cot inverse of cot x, this is equal to x when 0 less than x less than pi. Okay, so in interval 0 to pi, cot inverse of cot x, this is equal to x. Then sec inverse of sec x, this is a periodic function with period 2 pi. Okay, and sec inverse of sec x, this is equal to x when 0 less than equal to x less than pi by 2, or pi by 2 less than x less than pi. Okay, so when x lies in interval closed interval 0 to pi by 2 or pi by 2 to pi, then sec inverse of sec x is equal to x. Then cosec inverse of cos x, this is a periodic function with period 2 pi. Now cosec inverse of cos x, this is equal to x when minus pi by 2 less than equal to x less than 0, or 0 less than x less than equal to pi by 2. Okay, then see sine inverse of 1 by x. So what is sine inverse of 1 by x? How can you write sine inverse of 1 by x in terms of cosec inverse? So sine inverse of 1 by x can be written as cosec inverse x if x belongs in open interval minus infinity to close interval minus 1 union close 1 to open infinity. Okay, when your x lies in this interval, then sine inverse of 1 by x, this is equal to cosec inverse x. Okay, then cos inverse of 1 by x, this is equal to sec inverse of x if x belongs in open minus infinity to close minus 1 union close 1 to open infinity. Okay, so in this interval cos inverse of 1 by x, this is equal to sec inverse x. Tan inverse of 1 by x, this is equal to cot inverse x if x is greater than 0. When x is positive, then tan inverse of 1 by x, this is cot inverse x. When x is less than 0, means x is negative, then tan inverse of 1 by x, this is equal to minus pi plus cot inverse x. Okay, so when you have cos x is greater than 0, then this is cot inverse x. When you have x is less than 0, then you have minus pi plus cot inverse of x. Okay, now sine inverse x. Sine inverse x can be written in terms of cos inverse x as sine inverse x equal to cos inverse of square root of 1 minus x square. Okay, and this can be written in terms of tan inverse as tan inverse of x by square root of 1 minus x square, and you can write it as cot inverse of square root of 1 minus x square by x. Okay, so first you have sine inverse of x. Okay, sine inverse of x. So sine inverse x, if you want to convert into cos inverse of something, okay, for that what you do? First of all, you will draw and you will draw right angle triangle. Okay, and sin x function is basically perpendicular divided by hypotenuse. Okay, so uh, use that concept and convert sin inverse x into cos inverse something, and tan inverse of something, and cot inverse of something. Okay, so you should keep in your mind sin inverse x, this is equal to cos inverse of square root of 1 minus x square. This is equal to tan inverse of x by square root of 1 minus x square, and this is equal to cot inverse of square root of 1 minus x square divided by x. Clear? This is how you can remember. Then see, you can also convert sin inverse x into sec inverse of something. So sin inverse of x, this is equal to sec inverse of 1 by square root of 1 minus x square. Okay, and this is equal to cosec inverse of 1 by x if your x belongs in open interval 0 to 1. Okay, so you should keep in your mind here x belongs in open interval 0 to 1, then you can convert sin inverse x into cos inverse of something, tan inverse of something, cot inverse of something, and sec inverse of something, and cosec inverse of something. Okay, so remember this. Okay, and note this property, very important property, this is this one. Okay, and this one also very important property and very useful property. Okay, all the properties are very useful and important, but these two properties are very important properties. Okay, so you should keep in your mind all these properties. Now moving to the next. Then see here cos inverse x. So if you have cos inverse of x and you want to convert it into sine inverse of something. Okay, so sin square x plus cos square x equal to 1. Okay, from using that identity you can convert cos inverse of x to sine inverse of something. Okay, so cos inverse x, this is equal to sine inverse of square root of 1 minus x square. Okay, then see you can convert cos inverse x into tan inverse of something. Okay, so you can write cos inverse x, this is equal to tan inverse of square root of 1 minus x square divided by x. Okay, and this is equal to cot inverse of x divided by square root of 1 minus x square, and this is equal to sec inverse of 1 by x. Okay, so you should keep in your mind this property also. Cos inverse of x, this is equal to sin inverse of square root of 1 minus x square. This is equal to tan inverse of square root of 1 minus x square divided by x. This is equal to cot inverse of x divided by square root of 1 minus x square. This is equal to sec inverse of 1 by x. Okay, and this is equal to cosec inverse of 1 by square root of 1 minus x square if x belongs in open interval 0 to 1. And here you have to verify how we obtain. Okay, and due to lack of time we are not going to prove. Okay, so just we are revise all the properties of inverse trigonometric functions here. So note these properties and try to prove how we obtain these properties. Then tan inverse of x, this is equal to sin inverse of x by square root of 1 plus x square. Then this is equal to cos inverse of 1 by square root of 1 plus x square, and this is equal to cot inverse of 1 by x. And you can write tan inverse of x as cosec inverse of square root of 1 plus x square divided by x, and this is equal to sec inverse of square root of 1 plus x square if x belongs in open interval 0 to infinity. Okay, so here you have to restrict x in open interval 0 to infinity, then you will get these are equal. Okay, then see, for sine inverse x plus sine inverse y, so sine inverse x plus sine inverse y, uh, this is equal to sine inverse of x times square root of 1 minus y square plus y times square root of 1 minus x square. Okay, when mod x mod y is less than equal to 1 and x square plus y square is less than equal to 1, or x times y is less than 0 and x square plus y square is greater than 1. Okay, if it's satisfied, then you can write sine inverse x plus sine inverse y as sine inverse of x times square root of 1 minus y square plus y times square root of 1 minus x square. Okay, and but if you have 0 less than equal to x comma y less than equal to 1 and x square plus y square is greater than 1, then you can write sine inverse x plus sine inverse y equal to pi minus sine inverse of x times square root of 1 minus y square plus y times square root of 1 minus x square. Okay, and when minus 1 less than equal to x comma y less than 0 and x square plus y square is greater than 1, then sine inverse x plus sine inverse y, this is equal to minus pi minus sine inverse of x times square root of 1 minus y square plus y times square root of 1 minus x square. Okay, very important this formula. Okay, so just you have to remember here the condition. Okay, and for which condition, for which formula we can use, that you have to keep in your mind. Okay, understand? All you understand? I hope you will understand. Okay, very simple. Just here we are revising all the properties. Okay, now moving to the next. Then if we have sine inverse x minus sine inverse y. Okay, so if we have sine inverse x minus sine inverse y. Okay, and if we have the condition mod x mod y is less than equal to 1 and x square plus y square is less than equal to 1, or if we have x times y is greater than 0 and x square plus y square is greater than 1, then you can write sine inverse x plus sine inverse x minus sine inverse y equal to sine inverse of x times square root of 1 minus y square minus y times square root of 1 minus x square. Okay, and when 0 less than x less than equal to 1 and minus 1 less than equal to y less than 0 and x square plus y square is greater than 1, then sine inverse x minus sine inverse y, this is equal to pi minus sine inverse of x times square root of 1 minus y square minus y times square root of 1 minus x square. Okay, so you have to remember here the condition for x and y. Okay, and then here you write the formula for sine inverse x minus sine inverse y. When you have minus 1 less than equal to x less than 0 and 0 less than y less than equal to 1 and x square plus y square is greater than 1, then sine inverse x minus sine inverse y, this is equal to minus pi minus sine inverse of x times square root of 1 minus y square plus here minus, okay, minus y times square root of 1 minus x square. Okay, so this formula for sine inverse x minus sine inverse y, and here we have given condition for x and y, and for other conditions here we have the expression for sine inverse x minus sine inverse y. Okay, then see here cos inverse x plus cos inverse y, this is equal to cos inverse of x times y minus square root of 1 minus x square times square root of 1 minus y square. Here mod x mod y is less than equal to 1 and x plus y is greater than equal to 0. Okay, when mod x mod y is less than equal to 1 and x plus y is less than equal to 0. Okay, when you have x plus y is greater than equal to 0, then cos inverse x plus cos inverse y, this is equal to cos inverse of x y minus square root of 1 minus x square times square root of 1 minus y square. Okay, but if you have mod x mod y both are less than equal to 1 and x plus y is less than equal to 0, then cos inverse x plus cos inverse y, this is equal to 2 pi minus cos inverse of x y minus square root of 1 minus x square times square root of 1 minus y square. Okay, understand? All you understand? I hope you will understand. Okay, now moving to the next. Now see here cos inverse x minus cos inverse y. Okay, so when mod x mod y is less than equal to 1 and x is less than equal to y, okay, x is less than equal to y, then cos inverse x minus cos inverse y, this is equal to cos inverse of xy plus square root of 1 minus x square times square root of 1 minus y square. Okay, and when minus 1 less than equal to y less than equal to 0 and 0 less than x less than equal to 1 and x is greater than equal to y, then cos inverse of x minus cos inverse of y, this is equal to minus of cos inverse of x y plus square root of 1 minus x square times 1 minus y square. Okay, now see for tan inverse x plus tan inverse y. So when the product of x and y is less than 1, that means x times y is less than 1, then tan inverse x plus tan inverse y, this is equal to tan inverse of x plus y divided by 1 minus x times y. Okay, when x is greater than 0, y is greater than 0 and x times y is greater than 1, then tan inverse x plus tan inverse y, this is equal to pi plus tan inverse of x plus y divided by 1 minus xy. When x is less than 0, y is less than 0 and x times y is greater than 1, then tan inverse x plus tan inverse y, this is equal to minus pi plus tan inverse of x plus y divided by 1 minus xy. Okay, and then for tan inverse x minus tan inverse y. So when x times y is greater than minus 1, when you have x and y, okay, and product of x and y is greater than minus 1, then tan inverse x minus tan inverse y, this is equal to tan inverse of x minus y divided by 1 plus x times y. When x times y is less than minus 1 and x is greater than 0 and y is less than 0, then tan inverse x minus tan inverse y, this is equal to pi plus tan inverse of x minus y divided by 1 plus x times y. Okay, and when you have x times y is less than minus 1 and x is less than 0 and y is greater than 0, then tan inverse x minus tan inverse y, this is equal to minus pi plus tan inverse of x minus y divided by 1 plus xy. Okay, so you have to remember, okay, and you should keep in your mind these properties. These are very important properties in the point of view of JEE exam. Okay, then moving to the next. Now see another property, that is 2 sin inverse x. Okay, 2 sin inverse x is equal to what? When you have minus 1 by root 2 less than equal to x less than equal to 1 by root 2, then 2 sin inverse x, this is equal to sin inverse of 2x times square root of 1 minus x square. Okay, you can prove it. Then when you have 1 by root 2 less than x less than equal to 1, then 2 sin inverse x, this is equal to pi minus sin inverse of 2x times square root of 1 minus x square. When minus 1 less than equal to x less than minus 1 by root 2, then 2 sin inverse x, this is equal to minus pi minus sin inverse of 2x times square root of 1 minus x square. Okay, so you first have to separate for into different intervals. Okay, like minus 1 by root 2 to 1 by root 2, 1 by root 2 to 1 and 1 minus 1 to minus 1 by root 2. Okay, and for every interval you have to find 2 sin inverse x. So 2 sin inverse x, this is equal to sin inverse of 2x times square root of 1 minus x square for the interval minus 1 less than equal minus 1 by root 2 less than equal to x less than equal to 1 by root 2. Okay, and then 2 sin inverse x, this is equal to pi minus sin inverse of 2x times square root of 1 minus x square when you have x between 1 by root 2 to 1. Okay, 1 by root 2 less than x less than equal to 1. When x between minus 1 to 1 minus 1 by root 2, then 2 sin inverse x, this is equal to minus pi minus sin inverse of 2x times square root of 1 minus x square. Clear? Then see for 2 cos inverse x. So 2 cos inverse x, this is equal to cos inverse of 2x square minus 1 when 0 less than equal to x less than equal to 1. Okay, and 2 cos inverse x, this is equal to 2 pi minus cos inverse of 2x square minus 1 when minus 1 less than equal to x less than 0. Okay, understand? So you have to remember this formula also. Then 2 tan inverse x, this is equal to tan inverse of 2x upon 1 minus x square if minus 1 less than x less than if minus 1 less than x less than 1. Okay, and 2 tan inverse x, this is equal to pi plus tan inverse of 2x upon 1 minus x square if x is greater than 1. If x is less than minus 1, then 2 tan inverse x, this is equal to minus pi plus tan inverse of 2x upon 1 minus x square. Okay, so you can prove all the properties. Okay, so in your home do it. Okay, try to prove every properties how we obtain these properties. Okay, then see 2 tan inverse of x. Okay, uh, in terms of sine inverse. Okay, so when minus 1 less than equal to x less than equal to 1, then 2 tan inverse x, this is equal to sine inverse of 2x upon 1 plus x square. When x is greater than 1, then pi minus sine inverse of 2x upon 1 plus x square. When x is less than minus 1, then minus pi minus sine inverse of 2x upon 1 plus x square. Okay, understand? So you have to note all these properties, okay, in your notebook, and then you have to revise daily basis. Then moving to the next, then we have 2 tan inverse x in terms of cos inverse. So 2 tan inverse of 2 tan inverse x, this is equal to cos inverse of 1 minus x square divided by 1 plus x square. Here are 0 less than equal to x less than infinity. When minus infinity less than x less than equal to 0, then 2 tan inverse x, this is equal to minus cos inverse of 1 minus x square divided by 1 plus x square. Okay, so by using the formula of tan 2x, this is equal to 1 minus cos square x divided by 1 plus cos square x. Okay, so using this formula, you can easily prove 2 tan inverse x, this is equal to cos inverse of 1 minus x square divided by 1 plus x square. Okay, when 0 less than equal to x less than infinity. When you have minus infinity less than x less than equal to infinity, less than equal to 0. Okay, then 2 tan inverse x, this is equal to minus cos inverse of 1 minus x square divided by 1 plus x square. Now note some points. So if sin inverse x plus sin inverse y is equal to theta, okay, then cos inverse x plus cos inverse y, this is equal to pi minus theta. Okay, so if we have sin inverse x plus sin inverse y is equal to pi by 2. Okay, then everyone find cos inverse x plus cos inverse y equal to what? Okay, write your answer. You have sin inverse x plus sin inverse y equal to pi by 2. Then find the value of cos inverse x plus cos inverse y. For that, you will subtract pi by 2 from pi. Okay, and you will get the answer. So if we have sin inverse x plus sin inverse y equal to pi by 2, then cos inverse x plus cos inverse y, this is equal to pi minus pi by 2, that is equal to pi by 2. Okay, then see next note, if cos inverse x plus cos inverse y is equal to theta, okay, then what will be the sin inverse x plus sin inverse y? So for that, just you have to subtract theta from pi. Okay, so if you have cos inverse x plus cos inverse y equal to pi by 2, then sin inverse x plus sin inverse y, this is equal to pi minus pi by 2, this is equal to pi by 2. Okay, good, very good. Now see another properties, like 3 sin inverse x. So you will know the formula for sin 3x. Okay, so first recall the formula for sin 3x. Okay, and then see here the formula for 3 sin inverse x. Okay, so if we compare the sin 3x formula and here 3 sin inverse x, then you can get some similarity. Okay, so 3 sin inverse x, this is equal to sin inverse of 3x minus 4x cube if minus 1 by 2 less than equal to x less than equal to 1 by 2. Okay, when your x lies in interval minus 1 by 2 1 by 2 minus 1 by 2 to 1 by 2. Okay, then 3 sin inverse x, this is equal to sin inverse of 3x minus 4x cube. Okay, and if your x lies in 1 by 2 to 1 1, okay, 1 by 2 less than x less than equal to 1, then 3 sin inverse x is equal to pi minus sin inverse of 3x minus 4x cube. If minus 1 less than x less than equal to x less than minus 1 by 2, then 3 sin inverse x is equal to minus pi minus sin inverse of 3x minus 4x cube. Okay, understand? I hope you will understand, and you all know, okay, these properties, just we are revising, okay, all the properties. Now moving to the next. So before moving to the question part, please wait a moment. Now we will discuss practice question part. Okay. So see here question number 1. In this question, here we have, wait, now we will discuss practice questions 1, inverse trigonometric functions. Okay. So here see first question. In this question, we have to find the principal value of sine inverse of cos of 33 pi by 5. Okay, and we have given here 4 options. So you have to choose the correct answer from the given options. So everyone do it first yourself. Okay, and give your answer. Which option is correct? Everyone do it and give your answer. Very simple question. You can do it. Which option is correct here? For finding principal value, you have to take theta between 0 to 2 pi. Okay. Try it and write your answer in chat section. Everyone do it and write your answer. Very simple. Easy question. Do it. Which option is correct here? Take your time and do it. It will hardly take 1 minute. Okay. So within 1 minute, give your answer in chat section. Everyone do it and write your answer. Which option is correct here? Are you trying? Are you trying? Write your answer. Which option? Okay. I hope you got your answer. Now let's check which option is correct here. The correct answer is here option D. Okay. So first of all, match with your answer. Then see here formula and key points that we use here. So first key points is sine of pi by 2 minus theta equal to cos theta. Okay, you will know this formula, sine of pi by 2 minus theta equal to cos theta. We have studied this formula in trigonometric function chapter. Okay, then you know sine inverse of sine x, this is equal to x in interval minus pi by 2 to pi by 2. Okay, when your x lies in minus pi by 2 to pi by 2, then sine inverse of sine x is equal to x. And cos of 2n pi plus theta, this is equal to cos theta. Okay, now let's solve this question step by step. So first of all, we will write cos of 33 pi by 5 as cos of 6 pi plus 3 pi by 5. Okay, so here we can if we simplify 6 pi plus 3 pi by 5, then we will get 33 pi by 5. Okay, so basically we have written here 33 pi by 5 as 6 pi plus 3 pi by 5. So cos of 6 pi plus 3 pi by 5, this is equal to cos of 3 pi by 5. Why? Because you know cos of 2n pi plus theta equal to cos theta. Okay, by applying these points, and here we get cos of 6 pi plus 3 pi by 5 equal to cos of 3 pi by 5. Then you can write cos of 3 pi by 5 as sine of pi by 2 minus 3 pi by 5. Why? Because you know sine of pi by 2 minus theta equal to cos theta. Okay, so cos of 3 pi by 5, this is equal to sine of pi by 2 minus 3 pi by 5. Now pi by 2 minus 3 pi by 5, this is actually minus pi by 10. So you can write sine of pi by 2 minus 3 pi by 5 equal to sine of minus 5 pi by 10. Okay, and therefore sine inverse of cos of 33 pi by 5, this is equal to sine inverse of sine of minus pi by 2 pi by 10. Okay, minus pi by 10. So here you can see minus pi by 10 belongs in closed interval minus pi by 2 to pi by 2. So you know sine inverse of sine x equal to x when x belongs in interval minus pi by 2 to pi by 2. Here this value minus pi by 10 lies in this interval. So sine inverse of sine of minus pi by 10, this is equal to minus pi by 10. Okay, and this is our final answer. I hope you will understand. Do you have any doubt? Do you have any doubt in this solution? If it's clear, then write in chat section CLR. Okay, everyone. Is it clear to all of you? Can I move to the next question? Please respond. Is it clear to all of you? Okay. Now moving to the next. In this question, here we have summation from I equal to 1 to 20 sine inverse of xi. This is equal to 10 pi. Okay, and you have to find the value of summation from I equal to 1 to 20 xi. Okay, so first of all, use this equation. Okay, and try to simplify and try to find the value of xi. Okay, for I equal to 1 to 20. Okay, then you will get easily summation from I equal to 1 to 20 of xi. We have given a 4 options, so you have to choose the correct answer from the given options. So first of all, write your answer in chat section. Okay, so everyone try it yourself and write your answer. Everyone do it. Very simple question, you can do it. Try it. Everyone try it and give your answer. Which option is correct here? Everyone write your answer. Very simple question, you can do it. Are you trying? Try it. Try it. It will take hardly 1 minute. Okay, so within 1 minute give your answer. Everyone. Are you trying? Write your answer. Okay, good. So see, which option is correct here? The correct answer is option A. Okay. So everyone match your answer with the correct answer. Now see which formula and key points used to solve this problem. So here pi by 2 less than equal to sine inverse x less than equal to pi by 2. Okay, you will know the range of sine inverse x, that is close interval pi by 2 to pi by 2. Okay, and you know sine of pi by 2 is 1. Now let's solve this question step by step. So focus here. So here sine inverse of x1 plus sine inverse of x2 plus dot 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 plus sine inverse of x20. Here basically we have expressed the summation from I equal to 1 to 20 of sine inverse of xi as sine inverse of x1 plus sine inverse of x2 plus dot 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 plus sine inverse of x20, and this is given to us 10 pi. Okay, since we know minus pi by 2 less than equal to sine inverse x less than equal to pi by 2. Okay, so then we can get here sine inverse of xi is pi by 2. Here 1 less than equal to I less than equal to 20. Okay, so if we take sine inverse of x1, sine inverse of x2 and dot dot sine inverse of x20 all are equal to pi by 2, then pi by 2 plus pi by 2 plus pi by 2 up to 20 terms. Okay, you will get 10 pi. Okay, so sine inverse of xi equal to pi by 2 satisfied the given equation. Okay, and here we get for well I equal to 1 to 20 sine inverse of xi equal to pi by 2. Then you know sine pi by 2 is 1. So sine inverse of xi equal to pi by 2, it implies xi equal to sine of pi by 2. So xi equal to 1, where 1 less than equal to I less than equal to 20. Now take sum of x1 x2 up to x20. So x1 plus x2 plus x3 plus dot dot plus x20, this is equal to pi by 1 plus 1 plus 1 up to 20 terms. Okay, so 1 plus 1 plus 1 plus dot dot plus 1 20 terms, this is actually 20. So summation from I equal to 1 to 20 of xi equal to 20. Clear? And this is our final answer. So I hope you will understand. And now moving to the next question. Okay, in this question we have to find the domain of the function defined by the function f of x equal to sine inverse of square root of x minus 1. Okay, so you will know how to find the domain of the function. Okay, so try to find here the domain of the function f of x equal to sine inverse of square root of x minus 1. So everyone try it on your one. Okay, and write your answer in chat section. Which option is correct here? Everyone try it. Take your time and try it and give your answer. Which option is correct here? Try it. Okay, try to solve this and then find the domain of the function here. Basically here you have to find those x for which the function sine inverse of square root of x minus 1 is defined. Okay, write your answer. Very simple question, hardly it will take 1 minute. Okay, so within 1 minute give your answer. Everyone do it. Everyone do it. Which option correct? Write your answer. Give your answer. Are you trying to do it? Are you trying? Which option? Okay, let's check which option is correct here. The correct answer is here option A. Good. Yes, good. Here option A is correct here. Okay. Now let's see which are key points and formula used here. So you know, well, domain of sine inverse x is closed interval minus 1 to 1. Okay. So domain of sine inverse x is x belongs in closed interval minus 1 comma 1. So using this concept, let's try to solve this. Okay. So given function f of x equal to sine inverse of square root of x minus 1. Okay. And now use the domain of sine inverse x. So for domain of f of x, here square root of x minus 1 lies in the interval minus 1 to 1. Okay, that means minus 1 less than equal to square root of x minus 1 less than equal to 1. Okay, now squaring both sides, you will get 0 less than equal to x minus 1 less than equal to 1. Now let's simplify. So it implies 1 less than equal to x less than equal to 2. Okay, and therefore x belongs in closed interval 1 comma 2. Clear? So what we have used here, we use domain of sine inverse x is closed interval minus 1 comma 1, this concept. Okay, and then easily we calculate the domain of the function f of x equal to sine inverse of square root of x minus 1. Okay, very simple question. I hope you all understand. Now moving to the next. In this question, we have to find the value of cos of 2 cos inverse x plus sine inverse x at point x equal to 1 by 5. Okay, very simple. So everyone try it. Okay, so try it by yourself first and give your answer. Which option is correct? Everyone do it. Give your answer. Take your time and give your answer. Everyone. Everyone do it and write your answer. Which option is correct? Okay, I am giving here hint. Okay, so you can write 2 cos inverse x plus sine inverse x as cos inverse x plus sine inverse x. Okay, plus cos inverse x. Okay, and then try to recall the formula for sine inverse x plus cos inverse x. Everyone. Which option is correct here? Which option is correct here? Okay, good. Now let's check which option is correct. Yes, the correct answer is option D. Okay. So everyone match with your answer. Then see here formula and key points used. So cos of pi minus x, this is equal to minus cos x. Okay. And you know cos of cos inverse x, this is equal to x when x belongs in closed interval minus 1 comma 1. Now let's solve this question step by step. So we have the expression cos of 2 cos inverse x plus sine inverse x. Okay. So you can write at cos of 2 times cos inverse x plus sine inverse x minus sine inverse x. Okay, here we can write here 2 cos inverse x plus sine inverse x as 2 cos inverse x plus 2 sine inverse x minus sine inverse x. Okay, now you know, well, cos inverse x plus sine inverse x is equal to pi by 2. Okay, so use this. Then this is equal to cos of pi minus sine inverse x. Okay, And you know cos of pi minus x, this is equal to minus cos x. So cos of pi minus sin inverse x, this is equal to minus of cos of sin inverse x. Now since we have x equal to 1 by 5, okay, so now put the value of x equal to 1 by 5, then this is equal to minus cos of sin inverse of 1 by 5, okay. And now you know sin inverse of x, this is equal to cos inverse of square root of 1 minus x square, okay, that we have studied in our theory part. So just recall here, sin inverse of x equal to cos inverse of square root of 1 minus x square. So you can write sin inverse of 1 by 5 equal to cos inverse of square root of 1 minus 1 by 5 whole square, okay. So this is equal to minus cos inverse of square root of 1 minus 1 by 5 whole square. This is equal to minus cos inverse of 2 root 6 by 5, okay. And here 2 root 6 by 5, this value lies in interval minus 1 comma 1. So cos inverse of cos inverse x equal to x. So here cos inverse of 2 root 6 by 5, this is equal to 2 root 6 by 5, and here we have negative sign, so this is equal to minus 2 root 6 by 5, okay. And this is our final answer. I hope you will understand and it's clear to all of you. So now moving to the next. In this question we have to find the value of cos of tan inverse of sine of cot inverse x, okay. And here we have given 4 options, so you have to choose the correct answer from the given options. So first of all, try it by yourself and give your answer which option is correct here. Everyone try it, and give your answer. Don't worry to give wrong answer, okay. So if you make mistake, then you will learn, so don't worry to give any wrong answer. It's important to try, okay. So try it, everyone try it and write your option, which option is correct here. Which option is correct here? Try it, give your answer. Everyone give your answer. Okay, let's check which option is correct here. The correct answer is here option C, okay. So option C is here correct answer. Now see which formula and key points used to solve this problem. First see here, cos of cos inverse x equal to x. Here x belongs in closed interval minus 1 comma 1. And sine of sine inverse x, this is equal to x when x belongs in closed interval minus 1 comma 1, okay. Now let's solve this question step by step. So here we have cos of tan inverse of sine of cot inverse x, okay. So what we will do here, so first we let here cot inverse of x equal to alpha, okay, and it implies cot alpha equal to x, okay. Now you know the formula of cosec square alpha minus cot square alpha equal to 1, okay. From there you can write cosec alpha equal to square root of 1 plus cot square alpha, okay. And cot alpha you have x, so cosec alpha, this is equal to square root of 1 plus x square. And you know sin alpha is reciprocal of cosec alpha, okay. So sin alpha equal to 1 by cosec alpha, and you have cosec alpha equal to square root of 1 plus x square, so sin alpha equal to 1 by square root of 1 plus x square. And now alpha, this is equal to sin inverse of 1 by square root of 1 plus x square, okay. And now you can simplify cos of tan inverse of sine of cot inverse x equal to cos of tan inverse of sine inverse of 1 by square root of 1 plus x square. Okay, and here 1 by square root of 1 plus x square belongs in interval closed interval minus 1 comma 1. Okay, so simply you can write this is equal to cos of tan inverse of 1 by square root of 1 plus x square. Okay, clear? Now since here we first let here we let here tan inverse of 1 by square root of 1 plus x square equal to beta. Okay, and then tan beta this is equal to 1 by square root of 1 plus x square. Now you know sec square beta minus tan square beta equal to 1. Okay, so from that formula you can write sec beta equal to square root of 1 plus tan square beta. Okay, and you have tan beta equal to 1 by square root of 1 plus x square. So sec beta equal to square root of 1 plus 1 by 1 plus x square. This is equal to square root of x square plus 2 divided by x square plus 1. Okay, and here you know cos beta is reciprocal of sec beta, so cos beta equal to square root of x square plus 1 by x square plus 2, and now beta equal to cos inverse of square root of x square plus 1 divided by x square plus 2. Hence cos of tan inverse of sine of cot inverse x, this is equal to cos of tan inverse of sine inverse of 1 by square root of 1 plus x square. This is equal to cos of cos inverse of square root of x square plus 1 by x square plus 2. And here square root of x square plus 1 by x square plus 2 belongs in interval minus 1 to 1. So cos of cos inverse of square root of x square plus 1 by x square plus 2 equal to square root of x square plus 1 divided by x square plus 2. Okay, and this is our final answer. So I hope you all understand. Do you have any doubt? Is it clear to all of you? Is it clear to all of you? Can I move to the next? Is it clear to all of you? I hope it's clear to all of you. Okay. Now, see here this question. Look at this question. Here we have the equation tan inverse x minus cot inverse x equal to tan inverse of 1 by root 3. Okay, and here we are asking this equation has how many solutions? No solution, unique solution, infinite number of solutions, 2 solutions. Okay, so you have to choose the correct answer from the given options. So first of all, try it one and give your answer. Which option is correct here? Everyone do it and write your answer in chat section. Which option is correct here? Which option is correct here? Please do it and write your answer. Everyone, do it and write your answer. Everyone. So let's check which option is correct here. The correct answer is here option B. Okay. Now see which formula and key points used to solve this problem. So first note here tan inverse x plus cot inverse x equal to pi by 2. Okay. And then solve this question. So we have given tan inverse x minus cot inverse x is equal to tan inverse of 1 by root 3. Okay. And from this equation we have to find the number of solution. Okay. See, it in plus tan inverse x minus cot inverse x, this is equal to pi by 6. Why? Because you know tan of pi by 6 equal to 1 by root 3. So tan inverse of 1 by root 3, this is equal to pi by 6. And now naming this equation number 1. But we know tan inverse x plus cot inverse x is equal to pi by 2. Okay, naming this equation number 2. Now on adding equation 1 and 2, we get here 2 tan inverse x equal to pi by 6 plus pi by 2. This is equal to 2 pi by 3. And it implies tan inverse x equal to pi by 3. and it implies x equal to 10 pi by 3, and it implies x equal to root 3. That means it has unique solution. Okay, so option B is here the correct answer. So I hope you will understand, and you will understand all the steps. Okay, and it's clear to all of you. Do you have any doubt? If you have any doubt, then you can ask. Okay, if you don't have any doubt, then please write in chat section no doubt. I hope you all understand. Okay, okay. So that's all for today's lecture. So thank you for joining.
Hello students, in today's lecture we are going to learn about moving charges and magnetism, and this is theory part. Alright, this is our disclaimer. So let's see the trend analysis of JEE means of last 5 years. So overall weight is according to last 5 years of the chapter moving charges and magnetism is 3.61%. If we talk about yearly quotient distribution, so we can say in 2024 quotient asked from Lorentz force, number of questions 2, and if we talk about their difficulty level, so quotient was average. Okay, in 2023 quotient asked from magnetic fields due to a circular wire conversion of moving coil galvanometer into ammeter and voltmeter. Total number of questions 2, and their difficulty level, so we can say quotient was average. Similarly, in 2022 question asked from motion of charge particle in magnetic field, number of questions 1, and their difficulty level average. In 2021 question asked from moving coil galvanometer, number of questions 1, and their difficulty level average. In 2020 question asked from Ampere's circuital law, number of questions 1, and their difficulty level average. So these are the important concepts for the exam. Okay, in today's lecture we will focus first concept of magnetic field. After that we will discuss Biot-Savart's law and its applications. Then we will learn magnetic field due to circular current loop. Then we will discuss Ampere's circuital law. Then applications of Ampere's law. After that we will see force on a moving charge in uniform magnetic field and electric field. Then we will discuss motion of a charged particle in a uniform magnetic field. Then we will discuss magnetic force on a current carrying conductor. Then force between two parallel current carrying conductors. Then we will discuss torque. Then moving coil galvanometer, and last we will discuss some important terms related to moving coil galvanometer. So these are the topics which we will discuss in today's lecture one by one. Okay everyone, so our first concept of magnetic field. Let's see. So when you put a magnet in a magnetic field, it feels a push or a twist, force or torque. This happens because magnetic fields can push or pull magnets. Now if you bring a magnet close to a wire that has electric current flowing through it, the magnet feels a force too. Why? Because the current in the wire creates its own magnetic field around the wire. Okay, so the moving electric charges, that is current, create a magnetic field, and that magnetic field can affect magnets nearby. Okay, this is called the magnetic effect of current. In short, we can say electric current produces a magnetic field, and that field can push or pull magnets. This phenomena is very important. Why? Because it is the basic principle behind many electrical devices like electric motors, where magnetic forces are used to create motion. Okay, and if we talk about uh, practical implications, so we can say this phenomena is the basis for many devices like electric motors, where current carrying coils produce magnetic fields that interact with magnets to produce motion. Okay, clear? Next, we will discuss Biot-Savart's law and its applications. So let's see magnetic field due to a current element. So consider a small segment of a current carrying wire called a current element. So here we have a wire. Look at here in the diagram. This one we have a wire and a current element here, ideal. Okay. So the current element denoted by ideal at a point uh, P, we have to find out the electric field. Okay, magnetic field at point P. So this element produces a small magnetic field dB at point P in space. All right. So the point P is at a distance r from the current element. Distance r from the current element as shown in the figure. So we can say in the figure the current element ideal okay, uh, is shown with current I flowing through it, and the vector dl represents the direction and length of this current element. The point P lies at a distance r from the current element, where theta is the angle between dl and r. Okay, so let's see mathematical expression. The magnetic field dB at point P, at this point, at point P, due to current element IDL is given by the Biot-Savart's formula. Okay, so dB equal to mu naught IDL, mu naught I into dl cross r divided by r cube. Okay, here mu naught is the permeability of free space, and the important point, cross sign, this one, cross represents the cross product, cross represents the cross product, which means the magnetic field is perpendicular to both dl and r, and r cube in the denominator shows the magnetic field decreases with the cube of the distance. If we talk about the direction of magnetic field, so we can say the direction of the magnetic field dB created by the current element can be found using the right hand thumb rule. Okay, so point your right thumb in the direction of current I and curl your fingers around the wire. So your fingers point in the direction of the magnetic field lines and created around the wire. So there is a one more method, okay, or we known as screw rule. So the sense of dl cross r, sense of dl cross r is also given by the right hand screw rule. So look at the plane containing vectors dl and r. Okay, dl and r. So imagine moving the first vector towards second vector. If the movement is anti-clockwise, the resultant is towards you, and if it is clockwise, the resultant is away from you. Okay. Now we will discuss magnetic field due to circular coil and circular arc. So firstly, we will talk about magnetic field at the center of a circular coil. So consider a circular coil with made of wire with radius capital R and capital N number of turns, that is loops. Okay. So when a current I flows through the coil, it creates a magnetic field at the center of the coil. And the magnetic field B at the center of the coil is directly proportional to the number of turns N. The current I and inversely proportional to the radius R of the coil. So look at the formula. From this formula, I think all the concepts are clear. So B is equal to mu naught Ni divided by 2R. So this is the formula for magnetic field at the center. Now if we talk about the magnetic field uh, uh, at the center of circular arc. So we have this one circular arc. Okay. So now consider a circular arc of wire, circular arc of wire, which is a part of a circle. Okay, everyone, subtending an angle theta, as shown in the figure. The radius of the arc is capital R, and the wire carries a current I. Okay. Since the arc is only a portion of a full circle, the magnetic field it produces at the center is proportional to the fraction of the circle the arc covers. And this fraction is the ratio of the angle theta to the full angle of a circle 2 pi. So the magnetic field B at the center due to this arc is given by B equal to mu naught I divided by 2R into theta upon 2 pi. So this formula is very important. Okay, everyone. So here we have two formulas. First, magnetic field due to a circular current loop at the center, and second, a magnetic field B at the center of the arc. Okay. Now we will discuss magnetic field on the axis of a circular current loop. So consider a circular coil of radius R carrying a current I. Okay. And current I with n number of turns. We look at a point P located at a distance R from the center O of the coil along the coil's axial line, the line perpendicular to the plane of the coil passing through its centers. Okay. So the figures, this one shows the setup where the coil we can say, look at here, the figure shows the setup. The coil lies in the plane and the point P is on the axis extended outward at a distance R. Let's see expression for magnetic field at point P. Okay. So the magnetic field B at point P due to the coil is given by B equal to mu naught Ni R square divided by 2 into R square plus R square whole power 3 by 2. So now let's see behavior of the magnetic field for large distances. When the point P is very far from the coil compared to the coil's radius, that is when r small r is greater than radius, the coil behaves approximately like a magnetic dipole. In this case, the magnetic field simplifies to B equal to mu naught n I r square divided by 2 r cube. This shows the magnetic field decreases rapidly with the cube of the distance r from the coil. Okay? If you have any doubt, please ask in the chat box. Now we will discuss the concept of Ampere's circuital law and line integral of magnetic field. Before discussing the concept, remember a point, and that is the magnetic field around a current carrying conductor forms closed loops. Alright, now we will talk about Ampere's circuital law. This law states that the line integral of the magnetic field B around any closed path is equal to the permeability of the free space mu naught multiplied by the net current I passing through the area enclosed by that path. So mathematically, this is expressed as closed integration B dot dl is equal to mu naught summation I. Okay. So let's understand it with the help of a diagram. So here we have a figure shows a closed path with magnetic field B along the path dl. Okay. So several currents I1, I2, I3 etc. pass through the surface bounded by the closed path. Alright. Currents I1 and I2 are passing into the surface, whereas I3 is passing out of the surface, or vice versa depending on direction. Okay everyone, it depends on direction. So now consider the above diagram given. So the net current summation I is the algebraic sum of these currents considering their directions. For example, summation I equal to I1 plus I2 minus I3. Now here a question arises, and what is that? Question is why some currents are added and some are subtracted in summation I. Okay, think about it. So the answer is direction of current matters. The sign positive or negative assigned to each current depending on whether the current is entering or leaving the surface enclosed by the closed path. Okay. So if the current passes through the surface inward into the surface in the direction consistent with the loop's orientation, it is taken as positive. Alright. And if that current passes through the surface outward, so we can say out of the surface, okay, opposite to the loop's orientation, it is taken as negative. So I1 and I2 are currents passing into the surface enclosed by the loop, so they are added I3. Okay, I3 here subtracted, so they are added I1 plus I2, and I3 is a current passing out of the surface, so it is subtracted. Alright everyone, I think this is clear. Yes or no? So applying Ampere's law, the line integral of B around the closed path is closed integration B dot dl is equal to mu naught I1 plus I2 minus I3. Okay. Now we will discuss about applications of Ampere's law. So the first we will discuss magnetic field due to a straight current carrying wire. Okay. So let's see. Consider a straight wire segment XY. Look at here, XY. Okay. Carrying a current I. This one carrying current I. We want to find the magnetic field B at a point P. Okay. Located at a distance, located at a perpendicular distance R from the wire. And the wire has finite length, and the angle subtended from the ends of the wire at point P are phi 1 and phi 2 as shown in the figure. Okay. So the magnetic field at point P due to the finite wire is given by B equal to mu naught I divided by 4 pi r square sine phi 1 plus sine phi 2. Symmetrical point on perpendicular bisector. It means if the point P lies exactly at the midpoint of the wire, look at here, midpoint of the wire. Okay, this one. So P lies exactly at the midpoint of the wire's perpendicular bisector, symmetrically placed. Then the angles are equal. Phi 1 equal to phi 2 equal to phi. Alright. So the magnetic field simplifies to B equal to mu naught I divided by 4 pi r square into 2 sine phi. So solving this expression, you will be get mu naught I into sine phi divided by 2 pi r. When the wire is infinitely long, the angles phi 1, phi 2 both become 90 degree. Okay, phi 1 and phi 2 become 90 degree. This one. So sine 90 1. So the magnetic field at a distance r from an infinitely long wire is B equal to mu naught I divided by 2 pi r. Okay. So when a wire XY is semi-finite, it means it extends infinitely in one direction but has a defined and in the other. So consider a point P located near the upper end of the wire. So at this position, the angles between the wire and the point P are phi 1 equal to 90 degree along the wire direction at the end, and phi 2 equal to 90 degree perpendicular to wire. Okay. So under these conditions, the magnetic field B at point P due to the current I in the wire is given by the formula B equal to mu naught I divided by 4 pi r, where mu naught is the permeability of free space and small r is the distance from the wire to point P. Alright everyone. Clear? If the point P lies exactly on the axial line of the current carrying conductor, that is directly along the line of the wire, the magnetic field at P becomes 0. So we can say B equal to 0. And this happens because the magnetic field lines from circles around the wire and on the axis of the wire, the field contributions cancel out. Okay. Now, when a wire XY is semi-finite, it means it extends infinitely in one direction but has a defined end in other. Okay. uh, this one we already discussed. So when the wire of infinite length, then magnetic field near the end will be half that of at the perpendicular bisector. Next is the second application, magnetic field due to a thick cylindrical wire. Okay. So here the cylindrical wire having radius capital R is shown with the current I flowing through it. Okay. The point where the magnetic field is being measured is indicated at a distance small r from the center. So the magnetic field lines are shown as circles around the wire. The magnetic field formula inside the wire depends on small r, while outside it depends inversely on r. Okay, on r prime, inversely on r prime. Okay. So consider a thick cylindrical wire carrying a current I. The wire has a radius capital R and the magnetic field B varies depending on whether the point of observation lies inside or outside the wire. Okay, outside the wire, it means for a point located outside the wire at a distance r from the center of the wire where r is greater than radius, the magnetic field behaves as if all the current were concentrated at the center. So using Ampere's law, the magnetic field at this point is given by B equal to mu naught I upon 2 pi r. Alright. And if we talk about the inside the wire, so for a point inside the wire at a distance r from the center where small r is less than capital R, the magnetic field depends on the proportion of the current enclosed within a smaller radius r. Since the current is uniformly distributed over the cross section, so the enclosed current is proportional to the area pi r square. So the magnetic field inside the wire is given by B equal to mu naught I divided by 2 pi into r divided by radius square. Alright. If the conductor is hollow, that is no current flows in the center region. So the magnetic field inside the hollow part is 0 since no current is enclosed. Okay. Now third is magnetic field due to a solenoid. Let's see. A solenoid is a long coil of wire carrying electric current. Okay. So we know a solenoid is a long coil of wire carrying electric current. So when current flows through the solenoid, it creates a magnetic field similar to that of a bar magnet. All right. And the direction of the magnetic field depends on the direction of current flow in the coil. So look at here, we have a two faces, south and north. All right. So on the face where the current flows clockwise, this end behaves like a south pole of a magnet. Diagram A. On the other face where the current flows anti-clockwise, okay, this end behaves like the north pole of a magnet. Diagram B. Okay. So the magnetic field lines inside the solenoid are parallel and directed along the axis of the solenoid. This axial magnetic field is strong and uniform inside the coil. Okay. If we talk about the outside the coil, outside the solenoid, so we can say that the magnetic field lines spread out and resemble the field of a bar magnet with a north pole and a south pole at the ends. Okay. Let's see a magnetic field inside a solenoid, infinite length approximation. So for a solenoid that is very long, okay, ideally infinite length. So the magnetic field at any point along its central axis can be calculated using Ampere's laws. As we know the Ampere's law, B is equal to mu naught Ni. So where N is the number of turns per unit length. So the magnetic field at the end of the solenoid, that is B equal to 1 by 2 mu naught Ni. At the ends of the solenoid, the magnetic field is not as strong as the at the center. It is actually half of the half value found at the center. Okay. So when we comparing both, so this one is the half. All right. And this reduction near the ends is called the end effect. Okay. If we talk about physical meaning of end effect, so we can say the magnetic field lines of force spread out near the ends, so the field is weaker there compared to the uniform strong field in the middle. Now we will talk about the force on a moving charge in a uniform magnetic field and electric field. Okay. So this concept is important because charged particles experience forces when moving through regions where electric and magnetic fields exist simultaneously. If a charge q moves uh, with velocity v, all right, into the region where both electric field E and magnetic field B are present, it experiences a force due to both fields at the same time. So the total force F on the charged particle is F equal to Q into V cross B plus QE. Here the first term Q into V cross B is the magnetic force, whereas the second term QE is the electric force. Alright. The magnetic force is expressed as Fm equal to Q into V cross B, which is equal to BQV sine theta n cap, where theta is the angle between the velocity V and the magnetic field B, and n cap is the direction perpendicular to both V and B. Okay, and the electric force is straightforward, that is Fe equal to QE. Alright everyone. If we talk about the direction of magnetic force, so we can say the direction of magnetic force follows the right hand rule for the cross product V cross B. Okay, and if the charge q is positive, the force direction is same as V cross B, and if the charge q is negative, the force of direction opposite to V cross B. All right, everyone. Now let's see first case. Moving motion of a charged particle in a uniform magnetic field. This is a fundamental concept in electromagnetism, okay, that describes how charged particles behave when they enter a magnetic field. Let's see initial scenario. When a charged particle with charge q and mass m enters a uniform magnetic field B with velocity v that is perpendicular to the magnetic field direction, that is theta angle equal to 90 degree, the particle experiences a magnetic force. Okay, so the force on the particle is Fm equal to qvb. Okay, and this force acts perpendicular to both the velocity and magnetic field, causing the particle to move in circular path. All right. The if we talk about the radius of circular path, so we can say the particle moves along a circular path whose radius r, that is mv divided by qb, and this radius depends on the mass, velocity, charge and magnetic field strength. Okay, next is we can say using momentum, that is p is equal to mass into velocity, kinetic energy k, and accelerating potential difference v. The radius can be expressed as r equal to p divided by qb, or we can say mv divided by qb. So which is equal to, in terms of kinetic energy, it will be under root 2 mk divided by qb. All right, this is a very simple expression but important. On rearranging the terms, you will be get r equal to under root 2 into mqv divided by qb, which is equal to 1 upon b under root 2 mv divided by q. All right, where p equal to mass into velocity means momentum of charged particle, k is the kinetic energy of charged particle. All right, and v is the accelerating potential difference. These expressions relate to the radius to physical quantities like kinetic energy and potential difference. Next is time, period of revolution. So the time t for one complete circular revolution of charged particle, t equal to 2 pi m divided by qb. This means the particle completes a circle in this fixed amount of time. And the frequency nu, number of revolutions per second, is nu equal to qb divided by 2 pi m. And angular frequency omega is equal to qb divided by m, rate of change of angle per second. All right, everyone. All these formulas are very important for the exam. Okay. Here, in the first, radius of the circular path, mv upon qb. All right. Now, suppose you have a charged particle like an electron or proton moving inside a magnetic field. This magnetic field is uniform. It means it points in the same direction everywhere. Okay, so the velocity of the particle can be uh, thought of as having two parts. One part moving along magnetic field. Okay, we call this the parallel component V parallel. The other part moving perpendicular to magnetic field. We call this the perpendicular component, V perpendicular. Okay. The question arises, why do we break it this way? Think about it, everyone. Because the magnetic force only acts on the part of the velocity that is perpendicular to the magnetic field. The parallel parts keeps moving straight without any force acting on it. All right. The magnetic force causes the particle to move in a circle around the magnetic field lines because it always acts perpendicular to the velocity and magnetic field. And the radius r of the circular motion depends on how fast the particle moves perpendicular to field, its mass m, its charge q, and the magnetic field strength b. So the r will be r equal to m v perpendicular divided by qb. Okay. So the faster the perpendicular velocity or the heavier the particle, the larger the circle. The stronger the magnetic field or the larger the charge, the smaller the circle. Okay. Second, if the particle's velocity is not exactly perpendicular to parallel but at some angle theta, okay, the particle does not think at once. It moves forward along the magnetic field due to v perpendicular. Okay, it it circles around the magnetic field like due to v perpendicular, v perpendicular equal to v sine theta, we know. So this combined motion creates a helix, or we can say uh, spiral path, like a spring stretched out. Okay. So the radius of this helix is r equal to mv sine theta divided by qb. This is just the radius of the circular motion caused by the perpendicular component. If we talk about the revolution period, so we can say the time period to complete one full circle, one revolution around the helix is t equal to 2 pi m divided by qb. Notice this time does not depend on the velocity or angle. It depends only on the magnetic field, the particle's mass and its charge. Okay. And if we talk about the frequency, so frequency nu equal to qb divided by 2 pi m. Okay. The third case, when a charged particle moves in a magnetic field and follows a helical path, it is spiraling around the magnetic field lines while also moving forward along those lines. Okay. So the pitch is the linear distance. The particle travels forward along the magnetic field during one complete revolution around the helix. So we know the particle's velocity has a parallel component v parallel along the magnetic field. So the time for one complete revolution is t. Okay. So the pitch p is simply the forward distance traveled in time t. P equal to v perpendicular into t. Since v perpendicular equal to v cos theta, where theta is the angle between velocity and magnetic field. So when we substitute, we get p equal to v cos theta t. Okay. So using the expression for t equal to 2 pi m divided by qv, the full formula becomes p equal to 2 pi mv cos theta divided by qb. This one. So this is the full formula. Okay. And if the direction of v is parallel or anti-parallel to b, theta equal to 0 degree or 180 degree, and therefore f equal to 0, hence the trajectory of the particles is a straight line. Okay. Clear? Yes or no, everyone? Now we will talk about magnetic force on a current carrying conductor. So when a conductor carries an electric current and is placed inside a magnetic field B, it experiences a force due to the interaction of magnetic field and moving charges electrons inside the conductor. So consider a small segment of the conductor with length dl carrying a current I. So the small current element experiences a tiny force given by dfm equal to idl cross b. Here cross denotes the cross product, which means the force is perpendicular to both the direction of the current element dl and the magnetic field b. The total force on the entire conductor is found by summing integrating the forces on all such small elements along the conductor. So the formula Fm equal to integration dfm, which is equal to integration I into dl cross b. This integral accounts for the shape and the length of the conductor inside the magnetic field. Okay. And if we talk about the direction of the force, so we can say the direction of the force, direction of the magnetic force Fm can be determined using Fleming's left hand rule. So let's talk about Fleming left hand's rule. So align your left hand such that the thumb, okay, so forefinger and the uh, middle finger are mutually perpendicular. Okay, forefinger points in the direction of B magnetic field, middle finger points in the direction of current I, thumbs points in the direction of the force Fm on the conductor. So this is the Fleming's left hand rule. So using this we can calculate the direction of the force. Now we will talk about force between two parallel current carrying conductors. So two parallel conductors carrying current produce magnetic fields. We know this. So that magnetic field interact with each other, resulting in a magnetic force between them. This is a fundamental principle in electromagnetism and explains how current carrying wire can attract or repel each other depending on the direction of the currents. Alright. So magnetic force on one conductor due to the other. So look at here. We have two diagrams A and B. So consider two long straight parallel conductors separated by a small distance r. Look at here, small distance r. If we talk about the first conductor, so we can say the first conductor carries current I1, okay, and the second conductor carries current I2. Alright, I1 and I2. The length of the conductor under consideration is L. Now we will talk about direction of force. So the magnetic field produced by conductor second acts on conductor first and vice versa. So the force on conductor first due to conductor second is denoted by F12 and the force on the conductor second due to conductor first is F21. Okay, so according to Newton's third law, these forces are equal in magnitude but opposite in direction. That is F12 equal to minus of F21. Okay, and if we talk about the nature of the force, attraction or repulsion, so we can say if current I1 and I2 flow in the same direction, figure A, the force between the conductors is attractive. They pull toward each other. If flow in opposite direction, figure B, we can say force is repulsive. They push away from each other. Okay. Mathematical expression for force F. So we know the basic concept of force between two parallel current carrying conductors. So when two long straight conductors are placed parallel to each other and carrying currents I1 and I2, they exerts a magnetic force on each other due to the magnetic fields generated by each current. So the magnetic force F exerted on a length L of one conductor by other is given by formula is F equal to mu naught upon 2 pi into I1 I2 divided by R into L. Okay, and force per unit length, uh, we can say by dividing force F by the length small l, we get the force per unit length F naught. So F naught equal to mu naught divided by 2 pi into I1 I2 divided by R. This quantity is useful for comparing forces independent of the length of the wires. Alright, clear everyone? If the currents I1 and I2 flows in the same direction, okay, so we can say the force between conductors is attractive. It means what? It means they pull toward each other. And if the current flow in opposite directions, the force is repulsive. It means what? It means conductors push away from each other. Okay. Now we will talk about torque on a current carrying loop in a magnetic field. Okay. So we know the basic concept. When a current carrying loop is placed in a uniform magnetic field, it experiences a torque that tends to rotate the loop. This torque arises because the magnetic field interacts with the magnetic moment of the current loop. If we talk about the mathematical expression, so we can say torque tau equal to NIAB sine theta. So the magnitude of the torque tau experienced by a loop with n turns, current I, area A, placed in a magnetic field of strength B at an angle theta between magnetic moment and magnetic field. The formula is tau equal to NIAB sine theta. Here NIA is called the magnitude of the magnetic dipole moment M of the coil. Okay, and torque in terms of magnetic dipole moment, we can say using the magnetic dipole moment M equal to NIA, the torque can be written as tau equal to mb sine theta. In vector form, the torque is the cross product of magnetic moment vector M and the magnetic field vector B. So we can say tau equal to M cross B. Magnetic dipole moment of a current loop. So when a current carrying loop behaves like a magnetic dipole, the magnetic moment M of a loop of any shape is given by the product of the current I and the area A of the loop. So we can say M equal to IA. Okay. And for a coil with n turns, the magnetic moment is multiplied by n. So we have the formula M equal to NIA. Okay. Now if we talk about the direction, so we can say its direction is determined by the right hand thumb rule. Okay, magnetic moment of a current carrying coil is a vector. It means it has both magnitude and direction, and its direction can be determined by using right hand thumb rule. Okay, everyone. Now we will discuss about moving coil galvanometer. So what is a moving coil galvanometer? Tell me everyone. Yes, I'm expecting answer from everyone. What is MCG? The moving coil galvanometer is an instrument that detects very small currents, even as a tiny as a nanoamperes. It can also be adapted to measure larger currents and voltages by adding appropriate resistances in parallel to make an ammeter or in series to make a voltmeter. Okay. If we talk about the working principle, so we can say when a current I flows through the coil of the galvanometer, it experiences a magnetic force. Okay, and the coil has n turns, each area A placed in magnetic field of strength B. The current in the coil produces a torque that tries to rotate the coil, calling the deflecting torque. Okay, so the formula to calculate the deflecting torque, d tau deflecting equal to NBIA, and coil is suspended by a fine wire suspension fiber which offers resistance to twisting. This wire has a torsional constant K. When the coil deflects by an angle alpha, the wire produces a restoring torque tau restoring that opposes the deflecting torque and tries to bring the coil back to its original position. The restoring torque is tau restoring equal to K alpha. And when the coil stops moving at equilibrium, the deflecting torque equals to the restoring torque. So we can say K alpha equal to NBIA. So rearranging these terms, you will get alpha equal to NBA divided by K into I. So alpha should be Ki, where capital K is NBA divided by K, small k, is galvanometer constant. Alright everyone. Now some important terms related to moving coil galvanometer. Okay, that is current sensitivity, voltage sensitivity, and some of the conversions used in galvanometer are given below. So first is conversion of galvanometer into ammeter. Moving coil galvanometer, a very sensitive device that can detect tiny currents. But what if you want to measure larger currents like those in everyday electric circuits? The galvanometer alone can't handle a bit, or we can say galvanometer alone can't handle big currents because its coil is delicate and might get damaged. Okay, so we connect a very low resistance called a shunt resistor, denoted as S, as shown in the figure, in parallel with the galvanometer, which has resistance G. Why parallel? Because in parallel the current splits into two paths. The galvanometer coil only needs to carry a small fraction of the current, preventing damage. The we can see the rest of the current flows safely through the shunt resistor S. Okay, if the total current flowing in the circuit is I, uh, then a small current Ig, look at the figure, small current Ig flows through the galvanometer. Okay, Ig flows through the galvanometer. All right. The remaining current I minus Ig flows through the shunt resistor S. All right. Since the galvanometer and shunt are in parallel, both are in parallel combination, the voltage drop across both is same. So using the Ohm's law, voltage across G is equal to Ig cross into Ig cross into G, and voltage across S I minus Ig into S. Okay, because these voltages are equal, so we can say Ig cross G equal to I minus Ig into S. All right. So rearranging the above equation to find S, we can say S is equal to Ig divided by I minus Ig into G. This formula tells us how to choose the shunt resistance S based on the galvanometer resistance G, the galvanometer current Ig, and the total current I we want to measure. Since S is much smaller than G, okay, most of the current flows through the shunt resistor. Only a tiny safe current flows through the galvanometer coil, and this setup allows the galvanometer to measure the large currents without damage. Okay, so the scale of the galvanometer can be calibrated to show the total current I, turning it into an ammeter. Okay everyone, let's talk about the converting a galvanometer into voltmeter. A voltmeter is made by connecting a resistor of high resistance R in series with a pivoted type moving coil galvanometer G. So look at here, there is a resistance R galvanometer. Okay, so here we calculate the voltage sensitivity, which is determined by the deflection of the galvanometer per unit voltage applied. So from the circuit we can say Ig equal to V divided by G plus R. So rearranging this term, you will be get R equal to V divided by Ig minus G. So we can say current sensitivity. So the current sensitivity of galvanometer is defined as the deflection produced in the galvanometer per unit current flowing through it. So Si equal to alpha divided by I. So we know the alpha. So just substitute the value of alpha and I, you will be get Si. In terms of NBA, it will be NVA divided by K. Okay. Conversion of a galvanometer into voltmeter. So this is the illustration. If we talk about the voltage sensitivity, so we can say voltage sensitivity of galvanometer is defined as the deflection uh, produced in a galvanometer per unit voltage applied to it. So SV equal to alpha divided by V. We know that V equal to IR, and put this value in the above formula, then it will become SV equal to alpha divided by IR. Now since alpha upon I is the current sensitivity, so we can say SV equal to SI upon R. So this is the relation between SV and SI. After putting the value of current sensitivity SI, so we can say SV equal to NBA divided by RK. Okay, so this is the SV. All right everyone, any doubt? That's all for the today lecture. Thank you for your attention. In next lecture we will solve some practice questions based on moving charges and magnetism. All right. In next lecture. Yeah, based on the okay, good Varsha, good, very good. Okay, next class we will solve some practice question. Okay, that's all for the today. Thank you.